dear virtual attendees. Those who have joined as virtual attendees, please wait for 5 minutes. We'll start the session by 6:05.
Sure, no problem. Thank you.
Is it on? Pratik, can you hear me? This is Preeti here.
Hey, Preeti, I can hear you.
Awesome. So we can see you. Say a long sentence so I can check if we can hear you, okay? You're frozen at this point. Huh? I see. London.
Yeah, the video is frozen. The video is frozen.
Yeah, Pratik. Okay, you're moving a little. Say something.
Can you hear me?
It's a little
Barely.
choppy, Pratik. Can you do something?
Okay, let me reconnect once again.
Yeah. Yeah. He's in London, so I hope that. No, it's not. I bring my bottle of water. So so Pratik is here.
Good. So far, so good.
So everybody's here. We checked Hima and Prakash also. Is he back? Actually, yesterday after the session started, some 20 people joined. It was like 65 when it started. Then slower, built up to 104 one time it was. You're sweating or dripping? Yes, yeah. Yesterday was a little. Sorry, he can deal with it when I come back. Because I think Rudra will start in. No, he is third. We'll start off because I have to speak for a few minutes and all that. And Swapna and Rajneesh will go on for about 10 to 15 in person. Does it look bad if I... Okay, Pratik, we see you.
Can you hear me now?
Yes. You're a little bit in now we can see you very well.
Okay, sorry for delay. Yeah.
No worries. Pratik, you'll be just speaking, right? No slides. Sorry,
I have 2 slides. I'm happy to present. So that's not an issue.
Okay. So you're going third. You can share the screen when the time is right. Okay?
Okay.
Okay, cool. Sorry, I'm a disembodied voice because I'm not in the range of the camera. Okay, that's me. They're trying to, I'll wave at you so you can see me. Okay, see you back in a bit. Thank you. I'm going to keep it on. Good evening, everyone. Welcome to the third day of the IIT Madras Energy Summit. We're grateful to all of you for showing up after so many hours of intense discussions on energy. It is my pleasure, it is my honor, it's my privilege to be the moderator for the first session, or the first formal session of the day. We are going to be talking about carbon dioxide sequestration. We're going to be referring to what we think of as hard to abate sectors. This ride is going to be very different from what you're used to, so I really hope you will enjoy it. We have 6 participants. I'm the moderator. I'm Preeti Aghalayam. I always forget to introduce myself. I'm a professor in chemical engineering at IIT Madras. And it's my honor to invite now my panelists onto the stage. First, I'll start with Professor Rajneesh Kumar. Professor Rajneesh is from the Chemical Engineering Department at IIT Madras. Maybe you can give him a, yeah, thank you. Rajneesh, I want to seat you in this, if you don't mind. Yes. I should have put a little label on that. I would now like to invite Dr. Swapna Singha Rabha. I hope I have said your name correctly. I really love the name. So thank you for not needing my prompt to give her a show of hands. Thank you, Swapna, for joining us. And our Swapna, you want to know which seat is reserved for you, right? I think this is good. Thank you, Swapna. Now I'd like to invite Professor Arvind Kumar Chandran, also from IIT Madras. He's a familiar face to you all, of course, but more than that, he's a familiar voice to all of you. He's been in the back of the room. Also, he's been on Twitter. If you all saw the very nice social media post we made yesterday, that was Arvind. Arvind, I've reserved the seat closest to me for you, if you don't mind. I have 3 participants. Since my brain is now a little bit frozen, I'm going to read if you don't mind. 3 participants are virtual. I hope that they will come on video and wave at us and so on. I think you'll spotlight them if I'm not mistaken. So I know their names, it's just the designations I need to read about. We have Dr. Prakash Chavan. I do see him up there. He's a senior principal scientist and he heads the gasification and catalysis project at CIMFA, that's the Central Institute of Mining and Fuel Research in Dhanbad. So he comes from real coal country. We're happy to have you on board, Dr. Prakash. We have Dr. Bhima Shastri. He's only the designation I'm reading. He's the Division Director of Integrated Carbon Management at the Department of Energy. Washington, D.C. is his current, I think, geographical location. Also, the map in the back is not illustrative of anything. Dr. Bhima, maybe you can wave at us so that we know that's you.
Hi.
We're also very happy to have Mr. Prateek Bam. He's a co-founder of Carbon Clean Solutions Limited. And do I see you, Prateek? Oh, yes, we see him now. Prateek is tuning in from London, if I'm not mistaken. So his day has barely started compared to us who are really tired by the end of the long day. So this is us. This is 6 of them with good technical knowledge and me with the mic. So if you don't mind, I'm going to take a seat now and kickstart this session. Is that for me? Thank you. So this is how, so that you're ready, right? This is how we're going to do this session. We'll have a few presentations by our distinguished panelists in a certain sequence that we think makes sense. Lot of science, little bit of technology, a few vistas that have not, and a few motives that have not yet been discussed so far. Broadly, the things that we are going to hit, the things that we are going to question, I think are a handful of numbers that we've heard over the past couple of days. One that I want to pick up from day one is 100% renewables. We said 100% renewables, we are going to get there. There was a lot of discussion on what does that mean and how we are going to move to that and what are challenges and so on. We are going to talk about the interim period. So that's a very nice utopian future when we'll be at 100% renewables. But here we are in 2021 in this very nice green colored auditorium. And what does it mean in the current day and the immediate future as we move towards that utopian, sorry, I'm saying utopian, but it's probably a more realistic thing than utopian, goal of 100% renewables. The second number that I want to talk about is 2047. That really captured my imagination. Anyone remember what that was? It was a year. Net zero, not 100% RE. So yesterday we decided as a forum that we will shoot for net zero by 2047 because it's a nice number, 100 years after independence and so on. Also, Michael Jordan number of years before our Honorable Prime Minister has promised it. So I thought this is also a great thing to mention to you again. Now, these two things are going to be only feasible in the immediate future if you understand and appreciate the type of things we're going to share today. So today is not going to be, Arvind has promised he won't talk about this. It's not going to be about batteries, not about electric vehicles and so on, but the motives are different. I think I won't say much more. Our first speaker is going to be Dr. Swapna. She has a presentation, little bit of science, I think little bit of technology and future vistas and plans and so on as well. So first, Dr. Swapna for a few minutes. We have your slide queued up over there. Yes, please.
Can you hear me?
Can you tap? When you tap, we could hear. Yes.
Can you hear me? Okay.
Yes.
Checking if the slides are working.
Yes, we can hear you.
Oh, yeah. Okay, now it's working. Yeah, I have to be here. Okay, I can see that. Okay, first of all, I'm Swapna Sinharabha. Thank you for the introduction, Preeti. And first of all, I would like to thank the organizer of Energy Summit because they are giving young faculty an opportunity to talk in this panel, and it's really encouraging. So thank you. And today, me and my colleague Rajneesh will talk about how to tackle CO2 emission from the industry. Before going to the technology part, I would like to just give you some facts. Like, with the increasing globalization, industrialization, lots of infrastructure is increasing, building increasing, energy demands are increasing. With that, CO2 emission is also increasing. You can see from this diagram that global energy is increasing gradually from 1990 to 2021, and there is no sign of decreasing the CO2 emission. And with the increasing CO2 concentration, there are some facts like evidence that the climate is changing. So nobody can deny that. Even these are some evidence like global temperature rise, ocean warming, sneaking of ice sheets, then sea level rise and extreme events. These are reported by NASA, and we also experience these things. For example, a global temperature rise, 2016 and 2020 is the hottest summer, like a highest temperature is reported. And also there is reports that Greenland and Antarctic's ice is melting. So and also in the last, I think, couple of years, there are extreme events we have experienced. So we cannot deny the climate change, and we have to do to save this climate. So but with that, the CO2 emission, which is like the main source of CO2 emission, is coming from the power sector, industry, transport, and buildings. These forms are very necessary for like we need energy for everything, for even charging mobiles. So for everything we need like power. So power industry, we cannot deny that. In industry, chemical, cement industry, steel industry, that's also we cannot like retire. Transportation, it's again important, and buildings are important. So these four areas are quite important for our livelihood, for human being, for our development or for our industrial improvement. So we cannot retire these areas and go to like 100% renewable or like green energy. So how to do that? So right now in the present scenario, pretty quickly mentioned that what is the immediate solution? And I feel that the CCUS currently is the only option where you can still decrease the CO2 emission without cutting down the dependency of the existing power plant and the industry. So in this talk, we will talk about CCUS, which is carbon capture, utilization, and storage. So I will be talking about CO2 capture, and Rajneesh will talk about CO2 sequestration. This is a roadmap of how the CO2 CCUS means. So there is like a point source where the carbon is captured at the industry, like flue gas is captured, and then carbon is captured and it's sent to it's transported, and then it was sequestered to either in the ocean using CO2 hydrates or for enhanced oil recovery, and also it can be stored in reservoir rock, saline aquifer. So and it can be also utilized, CO2 can be further utilized to synthetic fuel, cement production, or also chemical production without producing CO2. That could be an ideal scenario. So these are the roadmap for CO2 capture and utilization. Okay, this way. It's not changing.
They can do
next slide, please. Now what are the technology available? One is a post-combustion, where the CO2 is separated after the combustion, after the power generated, whatever the flue gas out from the furnaces can be separated in C2, and then it was compressed and take to the CO2 storage sites. Another is pre-combustion, where CO2 is separated before combustion happens. And third one is the combustion is done with the oxygen. Then CO2, whatever generated, don't need to separate, it will be directly sent to the sequestration plant. However, this technology is agreed, but it needs improvement to widespread to deploy this technology to the industrial level. Why? Because the CO2 capture or sequestration, the whole technology is very costly, it's highly energy demanding. And we have to also find out how we can incorporate CO2 capture and the utilization part, then only we will be successful. This is again some numbers I gathered from International Energy Agency report, which is special report on CO2 capture. Till now, 21 CCUS plants are operating in the whole world, and there are a lot of under construction, and there are a lot of advanced development is going on. However, this is a world database, but wait. Regionally wise, there are still a lot of gaps are remaining. Only few countries are actively working on CCUS. You can see from this map. You can see also India. In this, this is a global status of CCS in 2020. Only one plant is reported here, which is Tuticorin, which is in Tamil Nadu. They are the first industrial scale carbon plant in India, and I think more of that, I think Pratik will talk about it. And the other, some small urea plant also using this CO2 capture and utilization. They converted the CO2 with ammonia, and then for the they produce urea. Most recently, the Tata Steel has, I think, has installed a capacity of 5 ton per day capacity, which is the first carbon capture plant for blast furnace. So only you can see only 5 plants has been reported till now in India. This is the status of India. We need to work more on this CCUS so that we can capture the CO2 and work to tackle the CO2 emission from the industry. So what are the options for CO2 emission? But there are a few. If it's gas mixture with high pressure of CO2, then we can use physical absorption, cryogenic distillation, and gas mixture with low pressure of CO2, then we can use membrane diffusion and chemical absorption. In industry, mainly it's focused on liquid sorbent and solid sorbent because of because a gas mixture with low pressure CO2, and also because its energy cost is less compared to the physical absorption. Oh, this way. Next slide, please. One more. There should be one more. No, go back.
Have we lost a slide?
No, I don't think so. The next one? Next one? Okay, maybe I lost the slide. Okay, anyway, there is 2 technology which is more industrially commonly used. One is liquid sorbent and another one is solid sorbent. However, the main, the solid sorbent, liquid sorbent technology, which is more matured and commercially it is widely used, all the 5 the Indian companies has used amine-based liquid solvent to capture the CO2. So liquid solvent is, however, the regeneration cost from the liquid solvent, like for example amine, is very high. And also another problem is that there is a solvent loss because of the evaporation. And also, since the liquid solvent, the corrosion and also the aerosol formation, those are the challenges when you use the liquid solvent for CO2 capture. And for solids, so compared to the solid sorbent, which is, I think it's emerging as an attractive CO2 capture technology, and it's giving a competitive, giving competition to liquid sorbent is solid sorbent, like CO2, CaO, calcium oxide, and for example, amide-based solvent, activated carbon, and also new technology, MOF. So that solvent is attractive because the regeneration cost is low, and also they are moisture friendly. For liquid solvent, you have to remove the moisture before it send it for carbon capture, the fuel gas. But here, the sulfate solvent, it is immune to the moisture effect. So, but these technologies, these are the challenges, then what are the R&D required to do that? I think the slide was missing, the important slide was missing, but I'm talking that we need to develop the advanced sorbent and solvent. This material for the sorbent and also new sorbent which will be less corrosive and which can be regenerate quickly. But less expensively. And another thing is that the reactor, process intensification of the reactor, so that we can control because these are exothermic reactions, we can control the temperature within the reactor, so the heat transfer can be uniform and we can control. So reactor modification or reactor process intensification of the reactor is another thing. So these are the R&D we are looking into, and IITM is the initiative taken development for advanced CO2 captures. We are working on material development like MOF and also the new sorbent material. And our CCUS group is it consists of 13 faculty. We are looking into from molecular scale to lab scale to see the absorption capacity, the process intensification, and then finally our aim is to do the pilot scale studies, so then we can transfer the technology to the industry. So these are the initiative started or the planned roadmap for CCUS work at IITM. And another CO2 capture technique, I think Rajneesh will tell. And I think I hand over to Rajneesh.
Sure.
Yeah.
I will do that.
Yeah.
Thank you, Swapna, for sharing these. I apologize for losing one of your slides. Rajneesh is going to use the same presentation. So Rajneesh, if you will go next. I believe that what we are talking about right now is a situation where we have carbon dioxide emissions. We accept that for India, for example, several billion tons of carbon dioxide emissions will be there every year. And what Swapna has presented is one part of the story about what to do with the emitted carbon dioxide. And if I'm not wrong, Rajneesh, you're going to take us to the next step with your sequestration.
Yeah, thank you.
Over to you, Rajneesh.
Thank you, Swapna. So, I'll also see. So, yeah, exactly what Professor Priti was talking about, that there is 2.5 billion tons of CO2 emission every year from India. So, we need to look for technologies which. Yeah, so let's come back to this slide. If you see here, we talk about.
Rajneesh,
Oh, sorry. Yeah, sorry. Yeah, I didn't realize it. Yeah. So we talk about direct CO2 capture from air directly. Now there is a challenge here that the concentration of CO2 is going to be quite lean, and this is one of the biggest challenge about CO2 capture and sequestration part, that the concentration of CO2 we deal with are mostly quite lean. Here we are talking about 500 ppm of CO2. So it's very simple that if you are trying to capture CO2 from a gas mixture where CO2 is only 1 in 2000, then you are going to work really hard to find that CO2. Let's assume that you have one of the best material around the world, which is going to capture this CO2. So even for one molecule of CO2, even if you need one molecule of other molecule which is going to capture this CO2, so if 2.5 billion tons of CO2 is being emitted every year, you need at least 2.5 billion tons of that material which is going to capture the CO2. And that material is not going to come from thin air. You have to basically mine it. You have to do something so that you can produce that much of material. In reality, you need at least 10 such material to capture one CO2 molecule if you are talking about capturing CO2 from a 500 ppm concentration level. So this is why this 2.5 billion ton, whatever we are going to emit, it comes from here, point source. So easier way to handle is to basically capture the CO2 from the point source. Here as well, you get concentration of CO2 anywhere from 5% CO2 to roughly around 15% CO2. Most of the power generation which is being done from coal in India typically produces around 10 to 15% CO2, rest being nitrogen and other oxygen and other gases. So if you are talking about capturing CO2 from 15% or 10% clean mixture, basically you need a chemical which can basically preferably interact with the carbon dioxide and do this in an efficient manner. So depending upon what is the concentration of CO2, you need different technologies which basically capture this CO2. It could be chemical absorption, it could be physical adsorbent, or it could be other. I am going to talk about that in just next slide. But once you have captured the CO2, you will have to figure out what to do with this particular CO2. For example, if you are having a material, suppose a metal organic framework, which you have somehow managed to get 2.5 billion tons or 10 billion tons of metal organic framework, which is going to capture this CO2, you can't really throw this material, you have to regenerate it. So that's another problem. Once you have regenerated this material by utilizing huge amount of energy, what you are going to do with the CO2, because you are not only regenerating the material, you are also getting back the CO2. So the next question is that the CO2 has to be sequestered. So there are multiple options. People talk about utilization. So this gray path is utilization, conversion, and non-conversion utilization of CO2. Non-conversion means basically you can use this CO2 for enhanced oil recovery. You can pump it under the seabed where you have oil which has been exploited already, but there are still some oil left. So you can basically pressurize this oil field to get more oil. One of the other options which I'm going to talk about is to basically pump this CO2 down below the seabed, not below the seabed, it's 100 to 300 meters below the seabed, and basically convert this gaseous CO2 into solid hydrates. This is what I will talk about in little detail. But before that, let me tell you what is basically hydrate. So hydrate basically helps you in capturing as well as in sequestering. So I'll talk briefly about the capturing part of it. What basically you do here, you see this is basically mix seawater. So one important point which I was trying to say, that you need a material which is in large quantity available, and we don't have any other material other than water which is available in such a large quantity. Rather than water, I should say seawater. So we have huge amount of seawater. You don't need any other material. You can just use seawater, mix it with CO2, and you can convert it into hydrate. What we see here is this number. If you see, it's unfortunately it's invisible. So if you are mixing,
Can we try to move that zoom bar, Miss Lisa, a little
but
bit?
that's fine. This number is also here. So if you see, if you are trying to dissolve CO2 in water, there is 1000 molecules of water for every molecule of CO2. But when you are at right temperature and pressure conditions, this mixture is going to convert into hydrate-like a structure, which is ice-like a structure. There, the concentration of water is 6 molecules per molecule of CO2. So you are basically increasing the density of CO2 when you are converting this water gas mixture into a solid hydrate. And you can basically dissociate it further, and you can get 1:100. So what basically you are doing, if you are getting a mixture of say CO2 nitrogen or CO2 hydrogen or any other gas mixture, does not matter. It's just a representative figure over there of CO2 and hydrogen. If you are forming hydrate with this mixture, what you have to do, you have to bring the gas and liquid water in contact with each other at right temperature and pressure conditions. And this will convert into ice-like hydrate crystals at low pressure, at low temperature and high pressure. Okay. What you will do is that one of the gas, mostly CO2, will go into the hydrate phase. So if you have a mixture of CO2 and hydrogen and you form hydrate, you have a gas phase which is depleted in CO2, and you have an hydrate phase which is enriched in CO2. And you don't need anything else other than water. You can use seawater, that also does not matter. So what basically you are seeing as a chemical engineer, if you see, can you go to the next? Yeah. So as a chemical engineer, what you see, if you are starting with say for around 15-17% CO2 hydrogen mixture in first stage, this is the gas phase composition, and this is the hydrate phase composition. In first stage, you get around 50% CO2 in the hydrate phase. If you dissociate this hydrate, and you can go for the, okay.
What happened?
Yeah, so you can go for the second stage of hydrate formation, and you get, oh, the sharing is not.
I award you 60 extra seconds, Rajneesh, for your presentation because of these tech difficulties.
Oh, okay, I'll try to finish with the time limit. Yeah. Yeah, so what I was trying to say, that if you have a mixture of CO2 and hydrogen, and if you are forming hydrate with this gas mixture, gas phase will get enriched with hydrogen, because CO2 from the gas phase will preferentially go into the hydrate phase, and the solid hydrate phase will get enriched with CO2. So you can basically, it's much easier to separate a liquid and solid and a liquid and solid and a gas rather than two gases. So once you have basically converted this gas into hydrate, which is basically a solid liquid mixture, you can very easily separate this to solid and liquid. Solid will give you CO2 after dissociation and also give you water back, which you can basically form the hydrate again. And if you're using seawater, you get basically pure water. It means you will have no salt once hydrate forms, because hydrate forms only with the water. So you are getting basically potable water if you do this. So you're not only capturing the CO2 and getting CO2 back, you're also producing fresh water out of seawater. So once you have this CO2, which basically is, yeah, so it's working now. There will be question about what is the economics of this process. So let me show you. See, when we talk about the conventional processes like amine, you see the capture cost is shown here with this red bar, and it's quite low because obviously CO2 is basic in nature. CO2 is acidic in nature, amine is basic. So you would see that they would interact much strongly and the energy requirement is quite low, but the regeneration cost is going to be significantly high. And that makes roughly around 20 to 25% of power penalty. Basically, if you are trying to capture the CO2 from a 500 megawatt power plant, basically roughly you are saying that 100 megawatt of that will just go in capturing the CO2. So that's the kind of energy penalty you pay, and it's right now it's very difficult for us to understand who is going to pay for this energy penalty. Whether the government pays, whether the user pays, we really don't know. And this is where the bigger challenge is. It's not that there is no technology for CO2 capture, but the problem is that who is going to pay for that cost, which is basically incurred in capturing the CO2. Hydrate process overall does not really look too bad compared to if you compare the amine process. It's much better than the membrane process. Talking about physical absorbents, rectisol, fluorochemicals, pyrrhusol, chilled ammonia process and all, the CO2 capture capacity is quite low compared to hydrates, which has a very high capture capacity. Roughly 38% of CO2 basically goes in hydrate phase. As I was showing you, 1:6 ratio over there. So the point I was trying to make that economics is not bad, and you should be able to basically capture this CO2. The bigger challenge is that we are talking about a crystallization process. So the kinetics of the reaction has to be enhanced significantly. And in our lab, we really do a lot of work on improving the kinetics. So if you have no additives in water, this is the rate at which hydrate formation will happen. In presence of additives, we can basically enhance the rate of hydrate formation significantly. So when you get around 30 gram of CO2 per gram of water within 10 to 15 minutes. So this is the kind of capture capacity you get. So what basically we have demonstrated that you get a gas mixture, you basically pump a gas mixture from this side, and these are all the multi-bed reactor, which is what we have patented. You see these beds are basically copper packing with water in there. Gas mixture comes in, one of the gas goes into the hydrate phase, and by the time you give enough residence time, you get a pure gas out of it. So basically you pass CO2 nitrogen gas mixture or CO2 hydrogen gas mixture, CO2 will go and form the hydrate, it will remain in the solid hydrate phase, and hydrogen will not form hydrate. So this is why hydrogen will come out from the other end. And the separation factor is roughly 98. It basically means that for every 98 CO2 molecule which you are going to capture, one molecule of hydrogen will also get captured. So basically the separation efficiency is quite good if you do this. So what we have done here, these are the hydrates which form on the bed. You see this, these are hydrates where you will mostly have CO2 and a very small amount of hydrogen. So what basically we have done by this, that we have solved this problem of point source capture of CO2. Now you can regenerate. Regeneration is very easy because hydrate forms at high pressure and low temperature. You come to ambient condition and hydrate will dissociate. And once hydrate dissociate, you are left with pure CO2 gas. What you are going to do with this pure CO2 gas, this is again hydrate comes in picture. So this is what we are trying to do. The next stage is this. This is the phase diagram of CO2 hydrate. This is the seabed. This is sea surface. And if you go below, you know the pressure will increase. So you are like around 1200 meters from the sea surface. So it's around 12 megapascal or 120 bar. Okay, this is the hydrothermal gradient. This is the phase diagram. So hydrates are stable over here and hydrates are also stable over here. This red line is geothermal gradient. What we propose that if you see there are methane hydrates under the seabed, millions of tons of methane hydrates are there under the seabed around the world. And these millions of hydrates are stable from millions of years. They are solid methane hydrate. They are stable for millions of years. It's there under the seabed, and I can show you an example of that over here. You see, this is hydrate which is below the seabed. So these methane, which is actually a gaseous molecule, has remained stable in solid methane hydrate form for millions of years. What we propose is that we can do exactly the same thing in this region. Here I don't want to touch, because if you have form hydrate over here, there will be a lot of water flux and hydrate might dissociate. I don't want to target this region. Targeting this region, what yes, effectively we are going to do is something which we already know, is this you would have seen shale gas exploitation or shale oil exploitation. What you typically do, you do fracking. You basically have this kind of infrastructure, you build horizontal well, you frack it to get the methane gas out of it. Okay, you do exactly opposite of that over here under the seabed. You frack it, but you frack it to pump the CO2 which you have basically captured from all your point sources. And this technology already exists. There is nothing you need over here. The kinetics of CO2 capture and all, we have done those studies in the lab. And this is what I'm going to show you. So what basically you need a pilot plant which can mimic the conditions which is under the seabed. And under the seabed, you need around 150 degrees centigrade. You need a temperature from 5 to 10 degrees centigrade. And then you basically have this injection well and production well kind of arrangement. So this is what we have in our lab. You have a CO2 cylinder, which basically supplies CO2 either in liquid CO2, gaseous CO2, supercritical CO2, depending upon what you need. You can basically have this over here. This is a heat exchanger, which will basically convert a gas to supercritical or liquid. You have a hopper, some small amount of additive you can add. This is a static mixture over here. And this is an injection well. You see, this could be an injection well, which is a vertical injection well. We can change this to a horizontal injection well. We can have another vertical injection well. So you basically study the kinetics of CO2 hydrate formation once you have injected CO2 either in liquid CO2 form or in gaseous CO2 form or in supercritical CO2 form, and see what rate the CO2 will form into hydrate. And then the other step is that you have to also understand, once you have formed the hydrate, you have to also convince the people that these hydrates are going to be stable. So what you can do, you can study by increasing the temperature of this bed to 5 degrees extra, 10 degrees extra, and see at what rate this methane, CO2 is basically going to dissociate. So you can basically do that, capture. So this is the pilot plant, a mini pilot plant which we have, where you have CO2 cylinder over here. And then you can basically do all the mass balance, capture the CO2, know the rate at which CO2 is being captured. This is the reactor. You see, this is horizontal wells. This is the vertical wells and horizontal well over here. And once you form hydrate, it looks something like this. So I'm not going to show you the data or how it looks, but then these experiments were done within few days, and you form pretty much significant amount of hydrate by doing this. So this is all I have for my lab. We will discuss these things anyway. Thank you, Preeti. Thanks a
Sure.
lot.
Thank you, Rajneesh. Very interesting results from your lab. We'll now switch gears a little bit and go to our friend, Mr. Pratik Bam, to give us a little bit of what they've done on the ground. I know that I promised to wrap up all the presentations by this point of time, and that's my mistake. I haven't, but that's okay. It's been interesting. Pratik, over to you. Slowly coming up. You want to say something while we wait for your slides, Pratik? Is it frozen? Is it frozen? Okay. Okay. Yeah. It's,
Can you hear me? Sorry.
yes. Here, also see your slides. Please go ahead.
Something is. Hi, Preeti ma'am. Can you hear me?
Yes, Pratik, we can hear you.
Great, great. Sorry for all these technical issues. Again, good to meet you, everyone. Thanks, Preeti ma'am, for inviting and giving me opportunities. I think in the interest of time, I will say Carbon Clean has started from IIT Madras sometime in 2008, when me and my other co-founder have won Pan IIT competition. in 2008, and that's a really long journey we have taken forward. It's really to really innovate and really reduce cost of carbon capture. There is a part of my bachelor's and master thesis at IIT Kharagpur, which has gone this company inception, and really we are making that huge impact in reducing cost of carbon capture right now. I'm based out of London and trying to really make sure that we innovate in that space and have a global ecosystem to operate. But in the interest of time, I would love to tell you a bit more about what Carbon Clean is, what we do, and how we have immersed so far in this space. I think this, for us, the approach is very simple and very straightforward. We are in the space of carbon capture. We are innovating that from last 13 years. But the way I want to build Carbon Clean is to lead the world's smallest industrial carbon capture. So people talk about big carbon capture plant, expensive things, take 24 months to really build those. I think our approach is pretty straightforward. Get a modular approach, reduce the size and footprint, get a multitude of scalability on a standard scale, which is 10, 100, 300, or 500 ton per day, and get the lowest cost of carbon capture, including CapEx and OpEx from a customer point of view. We are really innovating this kind of approach on a global basis with a lot of commercial opportunities, operating across 45 sites on a global basis. I think this is what our technical front is all about. We have 2 active projects in that space, and this smaller industrial carbon capture cyclone CC, which we are operating, funded by US Department of Energy and UK Department of Energy, to really support decarbonization and really innovate this infrastructure to really innovate in carbon capture space. The approach is pretty straightforward. How can you modularize this? How can you really reduce the footprint size so that hard to abate industries, which has been built in 1930s, 1940s, footprint is a massive issue. The land is a massive issue there. Can you deploy carbon capture in those industries and really reduce their carbon footprint? That's what the ambition Carbon Clean has really working on. Carbon Clean is innovating, is working on hard to abate industries, which has no solution other than carbon capture, which is steel, waste to energy, petrochemical and refinery, and and cement. And we are working with some of the biggest customer in that space. So really working to really establish carbon capture as offering in those industries. I think one of the slides we mentioned about, I think one of the earlier slide we mentioned about Tuticorin as a reference case. I think proud to say that we are the one who has made that successful. It's running from last 5 years. It's a carbon capture, full scale carbon capture plant in Tuticorin, which has been operated in 2016 with our customer Tuticorin Alkali Chemicals. The project captured more than 60,000 tons of CO2 per year from a coal-fired flue gases. But good thing about that is it's an on-site utilization to soda ash, which is a green product which being used by Unilever for their green detergent. So we are linking a complete supply chain for carbon capture. So we are capturing more than 90% of CO2. It's really a zero emission plant, which we have put forward. All the emissions they have, we just capture all the CO2 and convert into soda ash. I think second reference, I think again mentioned about Tata Steel. Again, yeah, we were instrument along with Tata Steel. It's really set up first of its kind CO2 capture for the steel industry. Again, it's a modular skid design process which we have worked on. It's a pilot project we have put forward for a large scale application, which we want to work with Tata Steel in future. But approach is the carbon is really feasible to capture CO2 from hard to abate industry, and that's what we have really proven at real industrial environment, and that's what Carbon Clean is all about, pretty much in that sense. Yeah, so this is like short slide about Carbon Clean and who we are and some of the references in India we are operating at this point of time.
Great. Thank you, Prateek. I liked your leading slide, which had the net zero words on it, which is what we are going for. And we started the session also with that. also picked up on your words, hard to abate sectors. Of course, you referred specifically to steel and cement industries for our audience who may or may not know. These two industries currently contribute maybe 15 to 17% of the total CO2 emissions, definitely in our country and across the world as well. So these are the solutions that have been discussed so far are definitely important. They have a place in our minds definitely, and also in practice. Speaking of hard to abate, and speaking of things that people hate and which are very bad and that have a bad rap, coal comes to mind, a very popular four-letter word to hate. And that brings us to the next talk in our panel by Dr. Prakash Chavan from Simfer. Dr. Prakash, if you can cue up your slides at this point and walk us through the coal to methanol success that you've had and what it means for India.
Yeah, thank you. Thank you, Dr. Preeti. Good evening to all of you. In this particular talk, I am going to concentrate on three important aspects, mainly related to gasification, high ash coal gasification. I will cover aspects related to understanding the coal resource. Then high ash coal gasification, what are the suitable technologies and what is the indigenous development program. Then what are the targets and strategy for gasification of Indian coal resource. Now coming to important aspect, when India is having abundant reserves of coal, it's true, but we need to concentrate on this part. Most of the reserves are having ash content about 35%. So when we talk about gasification of these resources, as such commercially proven technologies are not available to handle such a high ash content. Now, important aspects related to gasification or requirements, we can say, first one is suitable technology, definitely. But simultaneously, apart from the available suitable technology, specifically for a particular feedstock, operational philosophy plays an important role. Standard SOP cannot be utilized for gasification operation. Depending upon the fuel properties for particular type of gasifier, specifically or tailor-made operational philosophy is very much essential. And both these factors are dependent on coal characteristics. Means systematic understanding of the fuel is very much essential. So keeping in mind this particular aspect, we need to identify the important parameters, important characteristics. Around 10 to 12 important characteristics are there, including basically very basic proximate ultimate analysis. Ash content as well as ash properties plays vital role. Both these properties are important towards selection of gasifier. Then agglomeration or clinker formation type of operational issues. Also carbon conversion depend for particular type of gasifier. And we can say on this basis selection of the suitable gasifier. Apart from these surface properties, reactivity towards gasification, these properties, characteristics are also important for selection of gasifier, as well as blending of different feedstocks, different coal and biomass or even petcoke. Next to these properties, particle size distribution as well as shape, density, these factors are also important for design of gasifier. fluidization type of phenomena, as well as feed preparation, handling of the material, feeding of the material. So in summarized way, we can say systematic understanding of all these properties is very much essential, which is needed for selection of the matching gasifier, as well as modifying the feedstock to make it suitable for particular type of gasifier, either by washing or blending with different feedstocks, as well as pre-processing of the feedstock, means crushing screening strategy, what should be the feed preparation strategy, including all the basic requirements, phenomena like drying, briquetting, pelletization. So proper understanding is essential. On the basis of these characteristics, we have developed strategy, systematic strategy for selection of the suitable gasifier according to the feedstock. We are not going to discuss these details due to the shortage of time. Now going to, on the basis of this particular exercise, the background, Niti Aayog has decided to gasification potential mapping of the Indian coal resources, and this particular responsibility they entrusted to our organization along with CMPDL from Coal India. We have covered MCL, CCL and ECL subsidiaries of Coal India and analyzed all these samples from these mines for around 10 to 12 required properties, and we have prepared characterization matrix. On the basis of this characterization matrix, we have suggested matching gasification technologies, as well as what should be the utilization pattern and strategy to exploit these reserves. And we have submitted this report to Niti Aayog. On the basis of these particular inputs, Niti Aayog has planned two options for exploitation of Indian coal resources via gasification route. One is using proven technologies like entrant flow gasifier from say shale or cements. So using this particular type of gasifier, a few installations will be developed in India, specifically for production of fertilizer as well as methanol, using again high ash coal as well as low ash coal from certain subsidiaries. Fortunately, we have one installation in Odisha. It is using Lurgi gasifier, moving bed gasifier. Again, both these options use only low ash coal. So either washing or blending is definitely required. But Niti Aayog's plan was to develop indigenous gasifier where we need not to go for any washing or blending. And indigenous gasification development, gasifier development program initiated by Niti Aayog. Under this program, organizations like CSR Simper, BHEL, IIT Delhi Thermax joint venture as well as EIL, these are the stakeholders, and all these organizations are developing pilot scale facilities, gasification facilities suitable for high ash Indian coal resources specifically. Now we have installed facilities to these targeted facilities, and engineering output from these development will be utilized for demo scale plant development, and after that commercially proven gasifiers installed at different locations as well as indigenously developed demo plants will be compared for performance with the high ash coal resource, and better suitable, better performing will be taken forward for commercial exploitation as per the Government of India's target. So now coming to the development at CSIR Simper, we have developed 1.5 TPD oxyglone pressurized fluidized bed gasification facility. on the basis of our in-house expertise. This facility has been dedicated to the nation on 17th November of last year. It is having fuel feed rate capacity around 1.5 TPD, temperature up to 1050 degrees Celsius. We have tested high ash coal from 2 subsidiaries having ash content in the range of 40%. And successfully we have achieved CO hydrogen percentage in the range of 25 to 30%. This is quite a good achievement to fulfill the requirements for downstream application, say like methanol or fertilizer production. Carbon conversion was, this figure was also quite attractive. It was above 95%. Syngas yield was in the range of 1.4 to 1.7 nm³ per kg of fuel. And we have applied for Indian patent for this particular development. During this particular exercise, we observed that for operation of the particular fluidized bed gasifier, smooth control over the process parameter is very much essential. Next to this, flow rates of gaseous reactants, mainly oxygen or air, along with steam, we need to control very precisely in order to get the proper fluidization as well as thermal balance between the endothermic exothermic reactions inside the gasifier. We also observed that when we handle high ash coal, definitely ash generation rate will be on higher side. So it prompts, due to the shortage of carbon inside the bed, it prompts for higher feed rate, and this results in lower residence time for the carbon particle inside the bed, and it hampers the carbon conversion. So proper optimization of these parameters and capacity of the system is very much essential. Next important parameter we observed is the bed height. We need to maintain bed height above the certain required level. Then and then only we can get the proper conversion of the carbon particles, and we can get suitable quality syngas. Otherwise, unreacted gases or gasifying agents exits from the bed, and syngas becomes very dilute. Next important parameter is flow rate of the steam. Basically, steam acts as a moderator to control the bed temperature as well as to avoid the operational problems like agglomeration and clinker formation. So optimization of these parameters along with bed height, temperature is very much essential in order to adjust the heat generation by combustion as well as heat utilization by endothermic reactions, along with maintaining the fluidization. So this was the some few important observations. Now coming to the what should be the strategy to exploit the Indian coal resources, we can say understanding of fuel is very much essential. That's why gasification potential mapping of targeted reserves is needed. Then gasification technology selection, yes, we can go for entrant flow gasifiers, but definitely high temperature entrant flow gasifiers only. We cannot use refractory lined entrant flow gasifiers. Only membrane walled high temperature entrant flow gasifiers we can utilize. But that too after washing of the high ash coal resource or blending with low ash coal in order to bring down the ash content within desired level. Otherwise, we can go for oxyblown fluidized bed gasifier. Though it is not a commercially proven technology is available, but observed results are quite encouraging. So indigenously developed technology can be utilized to exploit these reserves. Definitely, we need to develop operational philosophy for each and every mine or resource. And for this particular exercise, we can utilize AI-based operational philosophy development program, so that we can conduct the gasification during commercial exploitation very systematically with complete automation. To minimize the generation of CO2 or to utilize all the majority byproducts, polygeneration is plays a key role, because important side streams are nitrogen and CO2 during gasification. While generating oxygen, definitely nitrogen generation will be there. And after CO2 removal, huge amount of CO2 will be there. So to utilize these two streams, definitely there should be integrated fertilizer plant, so that we can utilize nitrogen as well as CO2. And to utilize the waste heat or side streams of the heat, we definitely power generation module should be there. So when we target any gasification based plant, say for methanol or chemical generation, integration with fertilizer plant as well as captive power plant is essential, so that CO2 generation and waste heat utilization will be on better side. Then to make it more attractive,
Dr. Prakash, shall we take the last few points maybe in the
just 3
Q&A
lines
session?
only.
Yeah.
This is the last slide and 3 lines only.
Okay. All right. Thank you.
So to make the fluidized bed gasifier efficient, development of indirectly heated gasifier using dual bed technology separately for combustion and gasification phenomena is essential, so that we can minimize the oxygen generation related energy utilization, as well as we can minimize the CO2 separation and sequestration. Definitely we can get the CO2 in concentrated form, which can be further utilized either for value-added applications, or it can be taken forward for sequestration purpose. Yes, for generation of oxygen as well as separation of the CO2, as well as targeted hydrogen, CO. For this selective sequestration, membrane-based technology development and its integration with the along with conventional technologies will play vital role. Definitely co-gasification with biomass resources, RDF, we need to target. And in India, exploitation of lignite reserves also we need to take into consideration, apart from the coal reserves. So I think this is quite sufficient to discuss in the next session. Thank you.
Thank you, Dr. Prakash. It was very interesting, but it's good that you're virtual and not in person, because I suspect some rotten tomatoes are coming the way of all us coal gasification people from the audience. But it was very good to maybe pick up on one of the last things you said, which is CO2 to value-added chemicals. This is a slightly different strategy again from what we've been talking about. Again, accepting that we are going to make CO2, and what can we do with the CO2 that we are going to emit. So for that, I have my good friend. What he's promised without his knowledge is that his presentation is going to be short but super intense on CO2 to value-added chemicals.
So I'm not going to talk about user presentation, Preeti, for sure. Thank you.
Thank you for that.
Yeah. So I think
you can walk and talk also, Arvind, if you
okay,
want.
so I can be more dynamic.
Yes.
So either I can use the front, I'll walk around. So we have been talking about green energy and all those things for the past 2 days. But let me also say, like what Preeti said, we are going to accept that we are going to keep using our coal-based ones, our carbon-based fuels until 2070, as per the PM's ambition, when we will be converting to net zero. And yesterday, we also pledged that we will try to do as much as possible by 2047 to go to net zero. So until that time, we'll be consuming the hydrocarbon-based fuels for many systems, right? And we'll be emitting carbon dioxide. So one of the options that Rajneesh provided nicely is that to store them in the form of hydrates under the seabed so that we don't have the carbon dioxide in the atmosphere. That's a fantastic strategy. And there are also other options we will have to explore how we can possibly convert that carbon dioxide back to some value-added products. Because you can imagine when you talk about 2070 net zero, I talked about hydrogen quite a lot, but then you can be a bit slow in executing that plan. Whereas you're going to emit so much by 2070 or 2047, whichever the target you're taking, nation's target or this energy summit's target. And we're going to emit, and we have only short span of time to execute this carbon capture plan. We have really short span of time. And one is capture and store, other is capture and utilize. And what I'm going to talk about is capture and utilize. So how to utilize it? Can I use carbon dioxide as a kind of feedstock for some products? Yes, of course. There are many ways. Typically, when you're late in the evening, if you're in the last session, I know how difficult it is if you're partly sleepy and there's so much of light onto your eyes. And I think they intentionally made it to keep the panelist awake. That's a great thing. Yeah. So in the CCUS lab, we strategically set that capture and utilization domain where we convert the carbon dioxide to fuels, specifically methane, methanol, formic acid, and syngas. And we've been talking to a lot of industries. I think some of you might have heard this story before. So no one wants methane and methanol from carbon dioxide because the present methane and methanol from the ground is too cheap, and you're nowhere going to meet the price. And you'll be doing it fundamentally for your fundamental interest and publish papers and move on. And if you're going to pledge net zero or try to reduce the carbon emission by then, we really have to convert it to something else other than methane and methanol. And then we were more into that academic thought for 1 year. We seriously went to that so much of ups and downs, and we finalized on syngas and the formic acid. And in this CCUS center, we know how to make carbon dioxide to syngas. We also know how to make carbon dioxide to formic acid. Of course, this is still at a very early stage, so we have prototypes demonstrated, but then we have a long way to go in order to execute it. But how much that long way is going to be so serious? When I talk about hydrogen, as I said, it can be a bit slow in executing the plan. But when I talk about carbon dioxide capture and storage, capture and utilization, it has to be damn fast. And I think in the Energy Summit, along with the pledge we have taken yesterday, 2047 to net zero, we should also take a pledge on work so intensely on carbon dioxide conversion to something very, very useful. Thanks, Preeti.
Thank you, Arvind, for that very short and sweet presentation without slides. Now we have the last speaker of our session, Dr. Bhima Shastri, is going to give us I think a more broad perspective than what we've seen. Dr. Bhima, take it away. And you've promised 7 minutes at the most.
Okay. Sorry about that. Can you see my screen?
Yes.
Okay, perfect. And I'll try to be short in the interest of time. I know, we'd like to have some discussion here. And thanks for inviting me to this panel. I think the nice thing about going last is that, I can touch upon some of the things that the previous speakers have spoken. I know Rajneesh talked about this, the triangle that he had with industry and with government and with academia, right? So I'll kind of try to give you an industry perspective, which typically when you do that, it's like throwing cold water on R&D. I mean, that's from personal experience. But it's to be taken in a way that, as a challenge more than it is. So the picture that you have here shows the stripper that we have in a Houston facility, where a 250 megawatt coal facility is, basically we take the CO2 out, use the amine system, and that's the stripper that you see there, and then inject it into the ground in the Permian Basin to kind of recover oil. Now, there are a lot of positives about this. The CCUS says, there are, without CCUS, you don't have really a solution for where we want to go with the net zero by 2047, like it was decided yesterday, and also provide key options to address emissions. And there's a lot of positives to this. But the key thing has always been that, even though we've demonstrated this, and this has been in operation for the last 10 years, it's hard to have filled out. The potential for CCUS has really petered out, and we're hoping that 2021 has generated some momentum to get this back into the fold. We have seen a lot of high-profile project cancellations, and so we want to see what we can do from the U.S. and the Western perspective in terms of what we can achieve with CCUS. Having said that, there are a lot of challenges. If you look at the IEA, which the Department of Energy funds significantly, they talk about the 37 gigatons of CO2. Over the last 10 years, from 2010 on, we have actually captured less than 3 million tons of CO2 with an annual capture capacity of 40 million tons. And if you want to get to that net zero, which in the US we have a path to net zero by 2050, we're talking that we need to increase that to 1.6 billion tons in 2030 per year. So it's a tall order, and there are several reasons why CCUS is gaining momentum, and I'll quickly go through the three ones that I think are prominent. There's a recognition within the community these days to accept CCUS as really the only way to move forward if you want to get to that net zero. There is a growing interest in hydrogen, and I'll talk a little bit about two industries, actually steel industry where the hydrogen is of interest, and of course the petroleum industry where it's used for cracking, right? And what's happening is we want to get that low carbon hydrogen, we need to definitely couple that with CCUS. And then there are a lot of investment plans that have come on board. So again, I can dwell on each of these slides for a longer period of time, but I really want to have that discussion that Preeti really wanted to have with the entire panel. So I'll go through these slides really quickly, talk about steel, cement, and coal, which is what was covered here. The hardest emissions to eliminate. This slide is a little dated, but it's still the same. Cement and steel worldwide, the numbers are like 4 to 5% and 5 to 6%, sometimes higher. But the baseload electricity, which was typically nuclear and coal, is shifting to. So what do we do with that coal? So coal, cement, and steel are some of the things that we're trying to tackle here within the Department of Energy and see what is it that we can do. And I think the previous speakers have touched upon this. Within the Department of Energy, we are looking at coal as an alternate to other things that we could potentially do. Maybe use microwaves and thermal treat it to make it into clear pitch liquids, and you mix it with biomass and biochars to make intermediate materials like graphenes and nanoflakes and these porous carbons that can be used for different circuitry type of materials, and then take them to commercial applications. And these have all been shown. These are not cartoons in any way. They have been developed in the lab scale to some extent. And a lot of stuff coming out of that include these carbon electronics, membranes that have been developed at MIT using solid carbon. And we've also mixed some of these graphene with concrete to make it much stronger. So, and then I'll go to two other industries that we touched upon, the cement and the steel. What we are looking at here is that, it's all good that what has been talked about in terms of carbon capture, sequestration, what we need to do, but we also need to think about what the future of the cement plant is going to look like. This is something that McKinsey put together, where they use oxy-combustion, they talk about clinker substitution, they use alternate fuels. There's going to be oxy-combustion because, and through that, there's going to be NOx reduction. And there's a lot of new ways that we're thinking through in terms of, how we can make this green and digital. This is something that Department of Energy is really heavily investing in. And then we're looking at what the future is. I mean, the future is really in the innovations and durability, substitutes for cement, and what we can do. And again, I'd like to have this discussion, and we're running out of time. So I'll kind of skip through a couple of these slides and talk about the other big thing that we're working on, which is the steel industry. We're looking at potentially, the big thing there is, coking coal. We're looking at, if we are going to use less amount of coal, can we convert some of that existing coal to coking coal? It's just maybe a chemistry. The other thing that we're looking at is, of course, how do you reduce that iron ore through other means? Basically looking at non-renewable reductants like hydrogen plasma. We're looking at electrochemically reducing the iron ore. And then, there's some new techniques that we're looking at. We have an abundance of natural gas here in the United States. So is it possible to take those hydrogen atoms, use those for the reduction of the iron ore, and the carbon that's left over, use it for making the steel? These are all things that are novel. We're kind of funding this research, and we need to look at scalable and cost-effective solutions, high-performing and decarbonization strategies, and the kind of work that Pratik and others are doing are really the right way to go forward. So from an industry perspective, what I look at is, you need to involve industry, because even though it looks like they throw cold water on it, they bring the practicality into what we do with academia, with research, and all of that. So what I believe is a path forward for what we want to do with this with this energy consortium is to establish institutes, work with nonprofits, and create a network, work with the government groups also in terms of regulation, and have that balance between the supply chain, workforce, and R&D. What we are trying to do here is pretty much like that innovation ecosystem that I've shown on the right. And we fund these on 5-year intervals with industry sharing one-to-one cost. And we believe that this is how we can tackle maybe this entire thing about getting to net zero by 2047. I'll stop there, and so that Preeti can at least have a few questions that we can all kind of intake. Thank you.
Thank you so much, Dr. Bhima, for a very quick sort of overview on things. I did have, as you said, a number of questions written down, but I think my questions can wait. I'm assuming that the audience would like to have a little bit of mic time. So I'm going to hand it over to you. Just sort of lay the boundaries out a little bit. We've had 6 very good presentations. As always, we've spoken for longer than we intended to, but I think by now you know to expect that. The boundaries for today's session are that we are talking about sectors that have been touted as hard to abate. If we want to get to that net zero target, we have to work on these sectors in various ways. We have to work on the engineering practice within these sectors and do better in every step of the processes that are in these sectors, and also the very nice techniques that were spoken about in today's session on carbon dioxide capture and utilization and sequestration. With that, I hand over to the audience for questions you may have. I believe that we started the session late, so I think it's well within my rights to take a few extra minutes and eat into your dinner time. I mean, I take it as my right. So I believe that we have time for 4 questions. So who would like to be the first of 4?
So the question.
Sorry? I should take 2 online questions. Okay. So you're one of 2 questions.
Okay. I don't know if it's coming through. It's coming through, right?
Yes.
Yeah. So we're talking about net zero by any date whatsoever. We're talking a huge scale. So for huge scale means that these hard to abate guys, steel and cement and power, need point source capture. Now they also need then storage, but let's at least talk about capture for the moment. At what price of capture per ton, metric ton of CO2, do the excuses go away? That's the question. What is the price? Pratik, I saw your $30 number there. Others may not. You didn't key on it, but you threw it up there on the slide, so I'm going to use it. So at $30, 30 US dollars per metric ton, is it going to be enough where the excuses go away? And then the second part is, once you capture it, you got to put it away. Are we further behind on storage and utilization than we are on capture? And so that's my question. It's a two-part question.
From whom?
Well, it can be for anyone because the first question is basically economic question. So I would say it's for Pratik and Bhima.
Yeah, I'd like to even take really quick on that, Vic, is sequestration is probably the easier part in terms of economics. I mean, maybe anywhere from $2 to $10, depending. When we looked at sequestration, we have an atlas that we have developed here and across the world. There is probably 4,000 years of sequestration that's potentially possible. Now, when you go to add the actual sites, yeah, that number may come down, but but the costs of that are maybe $2 to $10. Now, Pratik has mentioned that $30 per ton. That is our goal. But currently, even the amine system that we have, where the one that I showed in Houston, is running anywhere from $45 to $50 a ton. So there has to be some significant R&D to bring that down. And I believe the break point is somewhere around the $25 to $30. That's a sweet spot. I'm not talking about just capture alone. 25 to 30 for carbon capture and sequestration. That includes the $2 to $10 that I'm mentioning, plus the carbon capture. There is plenty of place here for sequestration. We talked about other things, but I believe that's a sweet spot. $25 to $30 for both CC and S, the sequestration.
That's when the excuses go away, right?
Yeah, and I think the industry will become a partner, and then I think we will see others kind of come into the thing. And of course, the big elephant in the room is the carbon. What do we do with carbon pricing? That could change the equation a little bit too in terms of what we want to do with CCUS. Maybe the tolerance for that price will be a little higher if you start putting a tax on carbon. I'll stop there. Pratik and others may have other viewpoints.
Pratik, I missed Vikram's question entirely, but Pratik, if you have something quick to add as answer, I don't mind.
Yeah, sure. I think quick one from our side, because we are very close to the industry, and I think as a shareholder from Samex and Chevron in our company, we like a lot of other industry we are operating at this point of time. I think the way we see, and I think we have done a very great exercise with McKinsey again to really understand the market, what is the price point, all these hard to abate industries planning to pay. I think in Europe, let me talk about, because I'm very close in European and US as a geography as compared to India, because carbon price has increased significantly, and what industry are looking at this point of time, everyone want to decarbonize. I think the message is everyone want to decarbonize after this massive climate change, what is happening at this. They are looking for a cost where they put a decarbonized solution at the carbon capture, at the hydrogen, at the biomass, whatever. They have a roadmap for all three. All industry have a roadmap for all three. And they think which is the low cost possibility, and what is my carbon pricing which I'm going to pay, and still I'm profitable after putting that. I think that's the economics all industries are working at this point of time to really understand what the price is in terms of working on. Carbon price, I think last week it is $100 per ton, $100 per ton in Europe, which is very aggressive. Hopefully it will cost you $200, $250 in near future. So I think everything in future will make sense based on market scenario and market condition. But industry are practically thinking to really adopt which roadmap of decarbonization strategy should work on, and $30 is what US Department of Energy assessment is looking for all those industries right now.
Okay, great. Thank you. Sorry,
Pratik, that $30 mark really also, I think we're planning to include sequestration in that too. I mean, that's what the future is. Not just the capture part, but also the sequestration part.
Okay. Dr. Ashok, can I take the online question? It seems like a small one, and it's particularly to Rajneesh. It's about, is there any worry on stability of your CO2 hydrates? For example, if there's a small temperature fluctuation, do you anticipate any issues?
Actually, if you talk about.
Sorry, this is from Shri Kavya online. I just want to call out her name. Thank you.
So basically, when we talk about hydrates, these are hydrogen bonded water molecules, and hydrogen bonding is quite strong. So every bond which you break, it would require energy. So a small temperature change is not going to break any bond. Even if it breaks one, then the next bond would not break because it would need some extra energy. So yeah, but we have checked this at 5 degrees above the sea temperature, and still the hydrates are stable. So that's something which we need to. So 100 bar or 150 bar, even 5 to 10 degrees rise in temperature will not dissociate these hydrates.
Okay, good. I was right in thinking that this is not going to take much time. Over to you, Doctor.
Yeah, thank you, Preeti. This is a question, actually, it's nice that this question is for a different presenter, and this is on coal gasification. And my question is, I know India is dependent on coal. We got to keep working on different ways of converting coal. But the issue for me is if you gasify coal and then turn that into syngas at 25% yield, then try to convert to syngas. I spent 10 years of my life working on gas to liquid projects. We built a bunch of them. They're extremely expensive. So it seems to me that converting it, gasifying it and making syngas and converting it into something else is an awfully expensive way to go. Have we considered coal liquefaction instead? More straightforward.
I don't have a mic, but I'm assuming this is to Dr. Prakash.
And you yourself, Preeti, I know you worked on coal gasification.
Prakash, do you have? Actually, we are working on coal liquefaction as well. So hydrothermal liquefaction of coal to basically convert coal into liquid product. So, and it actually turns out to be slightly better economically compared to gasification and then converting into some other form of liquid or say methanol or something. So yeah, I agree with Ashok that liquefaction of coal itself is a much better option compared to gasifying and then liquefying it. Preeti, if you want to add something.
No, I'm just wondering if Dr. Prakash has anything to add to it.
Yes. When we try to compare indirect, say, liquefaction related aspect specifically, direct liquefaction and indirect liquefaction using gasification route. When we compare this, direct liquefaction requires very highly severe conditions, pressure as well as temperature. But again, whatever products we get, it is definitely mixed fraction. So downstream processing will be required, tremendous downstream processing will be required. But when we go for gasification based conversion, from syngas directly we can get desired product pattern, say whether it is specific chemical or say methanol or any targeted say DME. So these are certain advantages. Apart from this cost point of view, whether it is say direct liquefaction or gasification based process, capex requirement will be more or less same, because for direct conversion processes, severity will be on higher side than the gasification based processes. So capex will be more or less in the same range.
So, I believe it was Dr. Krishna who asked that question. You know, it's interesting that coal is the only thing that we dig up from the earth and throw directly into the boiler and do whatever we've been doing for the last 150 years. Every other ore that we take out of the earth, bauxite or iron ore, we process it first, make it into something before we get the final product. Not with coal, right? So this idea of liquefaction has actually been something that people have looked at. Definitely, the Department of Energy has looked at it significantly. Microwaves is one of the technologies that we are kind of investigating. There are some nuances to that. But I think definitely getting an intermediate thing between when you get it out of the earth and doing something with it before you make your final product should be something that should be investigated further, I think, and I think Rajneesh was right on top of that. It's coal gasification too, is another area where, you look at pre-combustion capture is going to be significant. So you still need capture, but the pre-combustion capture, the CO2 that you generate before you get the syngas.
So I'm going to request the panelists, both virtual and in person, to skip dinner for a little bit and answer the online questions. But we'll let the audience go after the last question by the gentleman with the mic in the back.
Am I audible? Yeah. I'm Saurav from CBEB. It's well known. My question to the panelists, it might be a bit myopic, but this is to the panelists in the future. What according to this scenario, right? India is a 130 crores nation, right? Where are we now? What should be the way forward? Because 2057 you have already decided, right? That should be the way. It will be zero, right? Now, coming to the normal scenario where we are now and making it forward for carbon capture, all these things, where can we? Are we still in this process? Or there are particular ways to change our vision? Because what I believe, there should be a quantum leap in the concept. What those panelists out there.
Are you referring to carbon capture in particular or decarbonization in general?
Both carbon capture and decarbonization. Where are we? Where are we now? Are we in that phase of making it a commercial success, or can we make it out in this?
Maybe two quick answers. You can take up the carbon capture thing, and maybe you can just talk about the.
Yeah, as I think everyone has rightly said, there is no challenge in carbon capture. It's more about the cost of the capture. And as I was also pointing out during my presentation, that who is going to bear that cost. So technologically, there is no challenge. Obviously, we have to figure it out how to do it slightly cheaper so that it's easier for the users. So I don't know what quantum leap we are talking about, but it's not going to happen next day. It has to, people will have to work together to get that or get there actually. So yeah, it's one way. There is nothing, no free lunch here. You will have to spend money to capture the CO2, figure it out how to spend lesser amount of energy and do the same thing.
Swapna, anything you want to add on carbon capture, quantum leap, and where we are going to jump into?
It's a truth that we are lacking or we are behind a bit, because as the facts that like only 5 carbon capture has been operated, and I think how much industries in India has, I think more than 1,000 industry we have if you combine. So, but there are a lot of initiative has been taken by the government. Also, a lot of institutes are working on it, and also there is a lot of initiative from the industry also coming. They have to decarbonize. So we are going forward to that goal, and hopefully we will achieve that.
Thank you.
Great. Arvind, you want to take the general where we are in our roadmap?
So I think in terms of utilization, I think the most ideal thing would be, like, for example, we now burn petrol, gasoline, and then we pump carbon dioxide, or we burn coal and pump carbon dioxide in the atmosphere. Can we convert them back to the hydrocarbons, usable hydrocarbons? That's the best way to go with. I think if at all there's going to be some quantum leap, this has to happen. Like essentially I burn hydrocarbon, I generate carbon dioxide, I regenerate back into hydrocarbon using renewable power. But where do we stand at the moment is the cost as well as the technology is not competitive at the moment to make the carbon dioxide back to the selective hydrocarbons. One of the key issues is that I think that CCUS as a part of the center, which we work on, is how to selectively convert to a specific product. And that is a kind of nightmare. And as Rajneesh and Swapna pointed out, it's not like kind of overnight business. I think the entire world is working on it. Maybe 5 years down the line, 10 years down the line, we may get to that point. And definitely for sure going to do a damage. I think although we have woken up and then said like we're going to decarbonize, but we are still going to keep pumping so much of carbon dioxide into the atmosphere. That's the ground reality. But at least we have started doing this decarbonization now. So 10, 20 years down the line, things may be much better.
Okay, that's a good question. Thank you for that. I'm going to close out this session for you all, but not for you on the stage. So 35 billion tons CO2, that's what we emitted last year. The year before, more or less the same number. I think there was maybe a small dip in 2020 due to whatever COVID related aspects. So I feel like we are kidding ourselves when we say, let's not talk about this element carbon at all and refer to elements like hydrogen when we are in the energy summit. So I'm really glad that this entire panel of 6 people took the carbon element head on and talked us through some good news, some potentially good news, maybe some definite quantum leaps required into the future. Your questions are valuable. We have several online. If you want to stay back and talk to us a little more, we'll be here for a few more minutes. But let me make a quick pitch for our next dinner, of course, is now on, and I know I'm holding you back from that. But our next session, which starts at 8:05, if nobody minds, is on technologies that are enabling our transition towards whatever lofty goals we have about decarbonizing and net zero and so on. So with that, I'll say thank you and hand over, shut off my mic and go in for dinner. Thank you. Oh yes, I do thank my panelists, the virtual ones, for taking the time, and also those that are here in person. I think you know their names, I won't repeat that. Prakash, Bhima, and Pratik, there are some. Can you see the Q&A? Can they see the Q&A box?
I believe we can.
Yeah, so if you click it, Pratik, for example, there are some, Anand Krishnamurthy has a specific question addressed to you. You can just click the type answer and maybe type it out over there. And I'll try to see if I can take it from the other. Swapna, so this question on top, fabulous efforts, Dr. Swapna, is solvent reaction kinetics, especially solid state, commensurate with expected throughput of CO2. That's what it says. Try to project it. Can you see that? Is the sorbent reaction kinetics commensurate with expected throughput of CO2? You can say, and we will type it here. Just a short answer is.
I think Anand is online, he says, and he can speak. He's the one who's asked most of the questions here.
We'll just do a quick round, Bhima. I don't want to take any more of your time. Pratik, if you can ask that question online, I'll just take a few select ones and then we'll close it. Dr. Chavan, you have a timeline for scaling up the pilot plant to TRL H9.
Yeah, actually, inputs from this our particular development will be shared with engineering houses, and it will be planned by Niti Aayog. There will be some consortium including engineering houses, say like BHEL or L&T, along with developers like us, and it will be taken forward for a demo scale level. So target is 2023. So let us see
33, you said?
23 for demo scale, and by 2030, 100 million metric ton of coal. Government's target is to gasify for different product patterns.
Okay, cool. I'll just say 2023 and they can come back for clarifications. Maybe we'll take this last question, Dr. Bhima. Base load of 32% without fossil fuel, is it possible at all? I think a quick yes.
Base load of 32% efficiency without.
Not if I don't think you had a pie diagram where you said base load is 30%. That one.
Oh, okay. I talked about baseload electricity and what I was doing with that was I was trying to focus on the three things, right? Steel, cement, and coal. So the baseload electricity, yes, it's somewhere between 33 to 35%. Some of the more efficient ones are 40%. Of course, that particular graph is a little dated and it had more of coal in there. But if you look at the current fossil assets, which are more natural gas based, the efficiencies are much higher. But the coal based one are 33 to 35% efficiency. That's without CCUS. And I was trying to mention there that there are alternates to CCUS that you can potentially do, and that's what my talk was about. Taking coal and doing other things with it and not burning it. And for the baseload part, go to nuclear, and for natural gas and other type of fuels.
Okay, I just put very short answers because it's also I've taken 15 extra minutes. I think we'll close it with that, and hopefully the audience, the virtual audience, or in-person audience have more or less. Okay, sorry, there's one really burning question I cannot avoid, so I'm passing the mic.
Prakash, you mentioned about graphene flake. Prakash sir, you mentioned about, am I audible? You mentioned about graphene flakes in sequestration. Is this available in lab scale? Have you done it here?
Hello.
Am I audible, sir?
What is the question?
You mentioned about graphene flakes in sequestration process, right? Graphene flakes.
Graphene, yeah.
I mean, yes.
I think it is
not in sequestration process, but
I think Dr. Bhima Sastry talked about, no. He talked about uses of the carbon which you can get from CO2. So you can have graphene and all. Yeah.
Yeah, you can mix it with concrete and make it stronger, basically.
Correct. Like a different strategy to make value-added products. We spoke about chemicals earlier, like formic acid and methanol and so on. He's talking about other products, including graphene flakes and so on. No, that was Dr. Bhima's presentation. Dr. Bhima, is that what level is that technology to graphene at?
Oh, so when you talk about technology, it is it is at the lab scale. I would say somewhere between a lab scale and want to make it into pilot. So we're looking at what we can do potentially with a pilot. So lab scale, it has been demonstrated. I mean, that you can actually get these at a reasonable amount, but it's just a matter of scaling it up. So that's the next step for us.
Cool. He seems satisfied, Dr. Bhima. So thank you so much. Thanks a lot, Dr. Bhima Shastri, Dr. Prakash Chavan. I know your schedules are quite tight, and at least for Prakash, it's reasonably late in the evening as well. very early to come. Bottom of my heart, thanks for joining us. I hope your experience with this hybrid mode was satisfactory. And I hope that your participation in the IITM Energy Consortium will carry on into the future. Have a great day.
It's been a,
Thank you very much.
thank you, Preeti. Really appreciate
Thank
this.
you, Preeti. Thanks everyone. Bye.
Bye-bye.
Bye.
Dear virtual participants, since the first session got over by late by 5 minutes, we'll start the second session exactly at 8:08. Dear virtual participants,
Yeah, thank you. Got it.
yes. The camera on the stage.
Hi Muruganandam. Hi Deepak.
Hi, Satya. It's still getting worse. I'll talk anyway. Yeah, the cough is getting worse.
All right.
Hi, Deepak.
Hi. Hello. How are you feeling better?
It's still the same. I'm still having cough. In fact, it's getting worse. The cough. Fever is down.
Is it
Cough is
just a
increasing.
weather?
Yeah, I think it'll take 1 week. It's just 4 days over. Just had to wait it out.
Usual cold and cough, maybe.
Yeah.
Yeah. So you're not going out much and stuff.
I'm staying in a room. That's it.
Okay. Yeah, it must be hard to participate also, you know. Yeah.
Yeah, luckily there is online. Otherwise, I was thinking I'll just cancel this because he said first it's only offline. So that changed things.
No, I didn't want to give Muruganandam the option, but
Why should you be cancelling it? Hi Murgi, how are you?
Hello, madam. How are you?
I'm doing
Doing
very
fine. After a
well.
long time, I'm seeing you.
I know.
Yeah.
Thanks to COVID, it has become very
Yeah, 2 years out, right?
I know. How's everything?
Yeah, doing okay. I'm just having some silly cold right now. That's it. Cough, not cold. Really. Yeah.
Don't call it silly. It is already troubling you.
Yeah. It's not COVID. That's why I'm saying silly. It's not that serious one.
I know these days it is so scary. Even a little one sneeze and then you immediately start getting alarmed, you know, on what is it.
Yeah, I asked the doctor and he said, no, it's not that. So
in fact, I don't know how many viral infections we must have gone and it would have gone.
Yeah.
Every little thing is so scary.
Yeah.
hi Sriram. Good morning.
Hi, Sriram.
Hi, Satya. Hi, Murgi.
Hey, thanks. You are the only one who's put up the IITM Energy Summit backdrop. All the virtual panels.
Of course, if I get one chance, I'll flaunt it. I also realized this is like a Godav reunion with Deepak.
Yeah. 3 Godav guys here.
I feel left out. Not fair.
So there are quite a few of us who feel left out. Goda is their hostel.
I know.
Yeah.
That. Don't worry. I haven't stayed in a hostel in IIT, but I've lived and grown up at IIT Delhi, so I understand all this.
Yes.
Deepak is an alum, Murgi is an alum, Sriram is an alum. Deepak is a prof at UCLA. Sriram
Hello,
works
Deepak.
at National Grid.
Hello.
Yeah, and Muruganandam is a prof here. And Dr. Anudaya Ganesh is CTO at Cummins and an adjunct prof at IIT Bombay.
Let
Satya, are we making
I'm
up some
sitting
time
A
or are
at
we?
Cummins, huh? I'm not sitting
Previous
A.
panel got delayed a bit, so we are 8 minutes behind schedule.
Okay.
So we don't have the opportunity to catch up at all. So all panels are running 8 to 10 minutes behind schedule.
So how long is this panel, Satya?
1.5 hours.
1.5 hours, 9:30.
Yes, 9:30. And then we have one more speech after that, and then we close. So we've decided we're going to run only midnight sessions.
So each person gets around 7 to 8 minutes and then some
So
discussion.
anyway, I will introduce, but yes, that's the idea. 7 to 8 minutes of open remarks, and then no presentations, just discussions.
Wow.
Yeah, Binu is here.
Satya, am I audible?
Yes, Deepak, you are audible.
So
Loud and
did I hear that we are making opening remarks, but we are not sharing any slides?
Yes.
Okay. Okay. I have them ready, but I can do without it. So it's okay.
I think let's do without slides. It'll be better.
Okay, got it.
Satya, I must say it's been very inspiring looking at a number of the research project examples, just the collection of it overall, each of the past 2 days and today. It's kind of like, yeah, it's good to bring these together and let everyone see the breadth of what we're doing.
Thank you, Sriram. So this is the person you wanted to meet, who does all the biochemical. He's quite keen on the he set up the. We just had a quick glimpse with your colleague. Yes, it's already there. We are actively looking for investment for a larger scale. I'm not so high tech because I don't. We should have that software. No, any camera will do that.
I'm just waving to say hi to my friends. Hi, Anuradha.
Hi.
This is Preeti. Hi, Murthy.
Hi.
Sriram, we haven't met. Deepak, we haven't met. I don't know.
Nice to meet you.
So how many do you have there in real and how many virtual? Typically at Cummins?
See, we just broke off for lunch, so I think 47 are just staying online. But here, before we, not for lunch, for dinner. So here about we have 70 to 75 people in person.
Wow, that's good. That's very good.
Yeah, first day we had about 150 attendees at the start and about 90 till the end. So it was folks stayed on. That's on the online side.
So on average, we're having retention of about 75 to 80 people in
That's very good.
all the sessions.
Very nice.
Okay. Good evening, everyone. Thanks for coming back quickly after that light dinner. And this is the last session for the day, for the entire event. So we want to touch upon quite a few important elements of all of these discussions we have been having, which we have not at all touched upon till now. So to do that, I invite my co-panelists who are first physical here, Mr. Vipul Tuli, Professor Vinu, all right. Okay, so let me get started with the introduction. So in our panel today, we have a couple of distinguished faculty members, industry stalwarts, experts who has opinion, which they will, I hope, share freely. First up is Mr. Vipul Tuli, who is the CEO, South Asia of Sembcorp Industries. Sembcorp is a large independent power producer in India, having, I think, over 4.5 gigawatts of assets in the traditional fossil-based industries, and also about 2 gigawatts of assets in the renewable industry. So he has a thing or two to talk about how this industry is evolving and what do we need to do more. On the virtual panel, we have Professor Dr. Anuradha Ganesh, who is the Chief Technical Advisor and Director at Cummins, also an adjunct professor at IIT Bombay. She has done the role of an academic, done a lot of academic work like what we do, now gone on to the industry, quite the opposite of what I did, spent time in the industry and came back to academics. So I believe she has quite a bit of opinions and pointers for us academics to consider and take it forward. We have Dr. Sriram Krishnan, Director of Strategy to Plant Process and US Gas Transformation at National Grid from the USA. Dr. Sriram. We have Professor Deepak Rajagopal, Associate Professor at the Institute of Environment and Sustainability at UCLA. He's an engineer turned economist turned activist, I would say, not activist yet. But we have all looking at technology choices without impact assessment. So his job is to tell us that the impact what we are creating and how do we avoid it. We have Professor T.M. Muruganandam, Professor of Aerospace Engineering, heading the Advanced Gas Turbine Concepts for Combusting Hydrogen. So I work with him. He's my co-collaborator in the Advanced Gas Turbine Center of Excellence. Here we have as a physical participant, Professor Vinu, Professor at Chemical Engineering. His specialization is in biomass conversion, thermochemical methods, and pyrolysis. So all of that we need to do to manage the interruptions that we generate from using renewables is something that probably will take Professor Vinu's help to manage. So that forms our panel, ladies and gentlemen. So let me get started with our opening remarks. The way that I would like to organize this panel is put out some statements from a recent commitment to COP26 by our Prime Minister, which is called the Panchamrit. I thank Vipul for sharing with me a brief back of the envelope calculations, because that really brought the numbers out. It is stark, it is quite challenging. I think we really don't know how to get there. So let's, the whole idea about this third session, this final session, is to talk about enabling the transformation. When we say enabling, it is through technology, economics, policy, and also the presence of pioneers who would take the step forward when there is too much risk. So in this case, let me put out the non-fossil commitments to be about 500 gigawatts by 2030. We heard that. 50% of that to come through renewable electricity. We've also heard that. And carbon emission reduction by 1 billion tons and carbon intensity reduction by almost 45%. And to do this, we are expected to add about 525 gigawatt of non-fossil sources by 2020. Now, let me start by asking Vipul. He's been out there in the field and facing the brunt of all these commitments. And we are probably armchair policy economists, not armchair technologists, but the rest of it. So Vipul, can you tell us what does it feel, or what an IPP like Sembcorp
see this green transition? What are the challenges you envision inherent in the interruptions that might come in renewables? Maybe more so by the commitment itself, what do you think has not been said or left unsaid that really needs to be addressed?
Can you hear me? Thank you. Thanks, Satya. Very happy to be here. Thanks for having me. And although this is the graveyard shift, but I'm happy to see many colleagues from overseas as well. And so I hope we have a good discussion. I think the best evidence of what a typical energy company is going through, Sembcorp is a very good example of that, because we are a mid-sized energy company committed to sustainable energy. Mid-size is relevant because we are not too big to fail or fully supported by a sovereign. We are also not so small that it's irrelevant and frankly, company mortality will take care of it. We are mid-sized, we are determined to succeed, and for us, we call it our brown to green transition. What that means is, if I look at our actual capacity mix, when I joined Sembcorp about 7 years ago, 6.5 years ago, we had about 12,000 megawatts conventional, almost zero renewable. Okay, that was 6 years ago. Today we are 4,500 renewable, 11,000 conventional. So almost 1/3, 2/3 kind of thing. In 3 years, it's going to be 2/3, 1/3. And if you actually think about the gut-wrenching differences that makes to how as you said, the technologies, but also the economics, the projects, the financing, the risk management, everything changes. The mindsets, the people, everything changes. It's like turning a company inside out. Right? If I had to think about what are some of the realities we are facing, okay, for us, number one, and I'm now not talking about the global company, but I'm talking about India. Let's face it, the first reality is that 80% of our energy is from fossil fuels or related today in India. Right? Unlike Europe that has good access to gas either from the North Sea or from Russia, unlike the US, which has access to shale gas, unlike even to an extent China, which has access to Russian gas, India has very limited gas. Bringing in LNG in the quantities we need is not really a real option. So the first thing is we need to figure out how we are going to transition this 80% fossil fuel. 80% fossil fuel means about, I'm talking capacity, but try and understand it in energy terms. For a 250 gigawatt grid, that means we've got 200 gigawatt equivalent, which is fossil fuel operating today. How do you transition that in a situation where demand is growing, let's say 4-5% a year? Right? Number one. Number two, if you come to the Panchamrit, the 500 gigawatt commitment that the PM has put out there, which I think is a fabulous energizing commitment. What that means is today we are building about, if I'm generous, I would say we are building about 10 gigawatts a year of renewable capacity in India on a good year. On a bad year, it's 8. So let's say 10. To get to, and our total non-fossil is about 150 today. By the time everyone gets energized, committees are set up, policies are made, policies change, things change, etc., you'll have about 7 years to do it, or maybe 8 years if you're lucky. Okay. So we're really talking about going from 10 gigawatts a year to 50 gigawatts a year. Okay. No country in the world except China has come anywhere close to that rate of capacity addition. By the way, in addition to the 50 gigawatts a year of renewable that we have to build about 30 gigawatts a year of conventional to support the renewable, because we don't have any real storage solution yet. And existing conventional is retiring, so we have to clean up. So that's the second sort of reality of it. And the third reality is, and it's difficult for me to say this as a power sector player, the power sector is bankrupt today. Okay. the issue of DISCOM viability is well known. Everyone talks about it, and DISCOMs are everyone's favorite sort of whipping boy, as it were. They're in a difficult position themselves for socio-political reasons and so on. But the other interesting thing I'll tell you, if you look at the generation sector, okay, the ROE of the generation sector over the last 3 years has been average about I think it is -1%. You don't build 50 gigawatts a year based on -1% ROE on existing assets. By the way, that is a combination of PSUs at about 8-10% and the private sector deep in the red. Today, everyone's taking great advantage of the massive liquidity all over the world and building renewables, many of them at tariffs which are supported basically by valuation premiums and so on. So the economics of the sector, the financial viability of the sector itself, I believe, is anything but proven. Right? Then the question comes, what are the technology solutions? Right? I think we've done the renewable industry has done an outstanding job of being able to go from 0 to 150 gigawatts in, I think, 15 years effectively. Of course, it was there earlier also, but the real scale up happened in 15. Meanwhile, the conventional energy sector has done an equally fabulous job of building what it's been able to build. I mean, the Indian national grid beyond generation is one of the most amazing human assets ever created. The copper plate that we've created at a 220, 400, 600 kV level across the country. Very few countries can boast of a grid of that kind of size, reliability, scalability. And now, of course, we are telling them, oh, by the way, I need a grid, another 50 gigawatts in Gujarat. I need it by next year. I know it takes you 3 years to do it, but I need it by next year because it takes me 1 year to do a wind farm. So the technology challenges are changing completely. So that's some of the stuff we are facing. If I had to make a few more comments on I think what is relevant for us to think about, okay, within the technological challenge itself, I would say fourfold. Number one, how do we transition the conventional plants? We had some very interesting discussions this evening with many of your colleagues, including I was at Binu's lab with Satya, and look forward to sitting down with him later on. What do you do with biomass to these plants? How do you improve combustion in these plants? How do you actually you can easily get, not easily, you can easily conceive of at least 5-10% lower carbon just by better combustion. How do you actually get some of that done? You can maybe take another 10, 15, 20, 30% out with biomass. How do you actually get that done? Nobody has ever tried it at this scale. Is it possible? Can India be the country that does? Secondly, storage. To me, the single biggest issue for us is storage. If you had to ask me the one technology that we have to crack, very, very interesting, energizing discussion as usual with Professor Junjunwala earlier this evening around scaling up storage solutions, whether it's chillers in the basement in a distributed mechanism, or it is actually cracking anything from flow batteries to lithium-ion batteries to any other batteries at the grid scale. We don't have the solutions yet. No one has a solution for a 200 or by 2030 maybe a 400 gig grid. Nobody has that yet. So, how are we going? I don't think it's a question of whether we are going to do it. The question is, how are we going to do it? Because if we don't do that, we're in trouble. I think number three, the ecosystem for photovoltaic and wind itself. Today, we have built a pretty good ecosystem for wind. Unfortunately, it's a terrible example of how not to run a financially viable manufacturing ecosystem, because half, if not more than half of our wind manufacturers are bankrupt today. So something about our system is not working that some of the best companies eventually get into trouble. Right? I don't need to name them. These are very well-known companies doing exceptionally good work, but most of them are bankrupt. On the solar side, it's fabulous that we are getting started, but we are just getting started. Right? Like the rest of the world, we are 90+% dependent on China. How do we get all the way back? One is, of course, just setting up the capacities, which is what the PLI scheme of the government is now doing, and doing pretty well. It's moved fairly fast, and I'm pretty confident in the next 18 months or so, we'll be well on our way as these capacities get set up. But where's the tech development? That's not our tech. That is just screwdriver tech. That is building the plants on someone else's tech. Have we actually innovated them? Have we really built it, right? And then the fourth one I would say is hydrogen. One of my former colleagues at McKinsey used to call it, and some of you maybe in the commercialization ecosystem may be more familiar with it than I am, which is what the peak of excitement and the trough of disillusionment and then some maturity of technology and so on, right? I think hydrogen is definitely going up that peak of excitement right now. Sure, as I sit here, we'll go through the disillusionment as well. The question is, how do we get to the other end as fast as possible and make sure that not just the viability but the scale up actually works. Final comment: we have to find a way to make scaling up of the industry, academia partnership work. When I was preparing my remarks for this evening, I was going to say I don't see too many successful models. I would take that back today. And I got to tell you, I'm really impressed by what I've seen today. The combination of IIT Madras for the early stage and the research park for the later stage scale up, etc. The combination of that, I think you guys have something deadly here. How do we actually have this kind of ambition, this kind of scale? Of course, we have to do. Right now, there's a lot of ambition and a lot of early work. How do we actually get this to churn out some of these technology solutions at scale? But how do we replicate this at least another 5 or 10 places across the country and support it with policy? Right? We haven't talked about policy, but as a developer, I could go on for another 2 hours on how important policy is and how a little tweak here or there can completely make or kill an industry. So I'll just stop there with those comments. Sorry if I've gone a bit over the time.
No, perfectly fine, Vipul. I think that really sets the context here that we have ambition. We do know we need to transition. We have technologies, but we need to scale it up, bring the cost down, make it viable, but also policy support is there. Here's one I would like to call Dr. Sriram Krishnan to talk a little bit about his approaches and the ones that you have seen successfully employed in using policy to enable such a transition. And I would like him to particularly address such questions like, should we wait for, say in India, Vipul just mentioned gas is not there. Maybe it is there, but we have not yet found it. We're talking big on green hydrogen, probably to soak up all the renewables that come in. Now, should we wait for green hydrogen to come in and become economically available before we start of utilization pathways, or should we develop technology for utilization before any of these other things happen? Maybe you can share some understanding on how transformation happens in other places and what are some successful models.
Sure. Thank you, Satya, and good evening to all the attendees at IITM and the virtual panel attendees. It's a pleasure to be here. As Satya mentioned, I'm at National Grid, one of the largest utilities across US and UK. And just as a caveat, my remarks here today are made in my personal capacity. I'm also a research affiliate at MIT, where I have an interest in the study of technology progression. So particularly more recently around Internet of Things, deep tech, and what I would say is the convergence of multiple technology options. We see parallels in energy industry as well, where the cost of energy is marginal cost of generation comes out to close to zero. So what does it enable? I'd make a few points. First, I love the session title in that it's enabling technologies for renewable transition. There are two things, right? There are a suite of enabling technologies, but then we still have to enable those technologies. It's a little bit recursive. And what I can also say is, if you go back to the presentation by Professor Junjunwala earlier around 100% renewable, there is a suite of options. Even Vipul's comment here looks at a suite of technology choices. They have different maturity levels. So what to do to enable each is it's not one size fit all, but you'd have to think of what is the approach you would take that suits the maturity level of the technology, the adoption of the market, and the economics that are being present. in my background, I've spent a good decade in the solar industry, where it grew from roughly about 3-4 gigawatts globally total installations to about 600-700 gigawatts cumulative. So in that span, there are a number of interesting things to observe in terms of what enabled certain markets, what did not. There are multiple policy instruments, and I'll yield to Deepak as he's the policy expert here. But in many cases, when we think of technology adoption in the market, I would say you need a robust technology, you need a specific use case, and a viable business model. You will need all three of them. I mean, all through history, if you observe it, for something like you can build technology, but if you want to make money out of it, you need all three of them. And as you do this, where you saw a lot of examples in the research presentations today are technology that are at the point of getting to become more robust. Use cases so far with solar and wind, because it's electricity and kind of we benefit from sort of transmission, like so long as you plug it in and you can consume it, it's a different story. But for battery storage or for hydrogen, for example, you have to start thinking about specific use case and a viable business model, right? You have to find a customer who's willing to pay, and there is a pain point that is being addressed. Where financing comes in is you to unlock scale, you will have to have the right cost of capital that makes pool of financing available to support these at scale, right? Like when we talk in gigawatts of deployment, we are already talking in several thousands or lakhs of crores of Indian rupees of investment. So, right, like where every bit of this puzzle needs, at the end of the day, low cost of financing to unlock. I mean, even Vipul touched upon that. There was a specific question, should we wait about hydrogen? Again, not the expert specific to hydrogen. From what I've understood so far, right, you have, with hydrogen, you have to look at the entire value chain. There is challenges and around production, there is shipping of it, and there is the end use of it. You can't, the cost of production is very high today. So there are some specific use cases where long duration storage or hard to abate sectors like steel, where the use, even the cost is worthwhile pursuing, because the kind of outcomes are justified, and the economic value is net improved that way. So from that standpoint, if you ask me, I would say you can't wait for one step of the puzzle to solve the entire value chain. You'd have to take steps across the value chain. Even just in the last 2-3 days, there was a pilot project announced in the US Northeast. Just yesterday, there was something announced in Andhra Pradesh as well, where specific use cases around taking renewable generation, electrolyzers, and direct either a consumer use or a blended supply within the infrastructure that is there. But these are all like really small pilots. For the scale we are talking, like you need to accelerate the pace of such experiments. That will be my answer. And on cost, right, today costs are for hydrogen is maybe $20 a kilogram. I mean, the exact numbers, I may not be aware of the latest specific ones, but if you look at targets, the US Department of Energy put out a roadmap saying we need to get to about $2 a kilogram, where it starts to unlock a number of use cases. On the EU side, there have been similar efforts where they have said you need $1 per kilogram for hydrogen to be competitive with, for green hydrogen to be competitive with other blue or gray hydrogen, where you still have the carbon emissions as a challenge. But if you really want to compete with natural gas, it's about 40 cents per kilogram. So there is a long way to cover. But here, there are some lessons from history that can be beneficial. So there is an empirical tool called the experience curve that talks about what happens as technology scale up, right? It started with observing what happened to the Ford Model T cars costs. The general expectation is that as we double the production, you learn more from the experience of doing it. There are more people innovating. There are operational efficiencies, and that you would start to see the costs coming down. More recently, you also see the value of R&D. So there are three specific examples, I would say. If you look at solar, it started with NASA's satellites way back in the 50s and 60s. In mid 70s, that's when solar started to have commercial deployment. In about the 45 years since, you can see a natural progression of solar's experience curve around 20 to 22% in cost reduction. At different times, it was driven by R&D, I would say more in the 70s, 80s, and 90s. And then in the 2000s, I will say it's driven more by production scale-ups, manufacturing efficiencies, operational efficiencies, and deployment. Another example I would say will be LEDs. While we are talking about generation technologies, LED as an energy efficiency tool is something to be proud of in terms of what India had done, because policy-driven demand in India is attributed as one of the factors that caused a large enough need that suppliers came into the market, became more competitive. It drove down LED's experience curve. A third example is around battery storage. Vipul mentioned that as another area where there is still a suite of options, but in assessing, I recently saw a publication from Professor Jessica Tranchik's group at MIT, where they said R&D, right? They could look at the reported volume and types of battery storage technologies being announced and their costs being reported, and showed that R&D had a outsized effect on driving that experience curve down. So if I look back at these comments and say, do I have a crystal ball for green hydrogen? I would say I'm optimistic that the early projections of green hydrogen's learning rates of about 20% could be viable. There is, given where things are with small pilots, I would say there is a lot of scope and room for R&D. But I'd also like to be hard-nosed to say, for those learning rates to be sustained, you'd have to really hone in on the specific use cases where it is viable, where you demonstrate the economic value, you convey the storytelling to the broader audience, get industry excited so you can scale up, you get financiers excited so that lowers the risk perception and the cost of capital. I'll pause here. I see all of us kind of coming into this question around what do we do with these sort of suite of technologies, and I'm excited for the Energy Consortium as one of the ways where we bring folks together. It's not a one size fit all. It's not one solution for any one kind of broad set of opportunities. So it's a right way. It's almost a market clearinghouse approach as we think of interdisciplinary research and multiple use cases.
Thank you very much, Sriram. So that brings me this question: are we putting too much emphasis on hydrogen? So, like this question is, this discussion is addressed to you, Vinu. Where are there other intermediate pathways where biomass to fuel becomes the dominant strategy? Maybe third generation biofuels such as algal biofuels or any such mix. Can existing refineries do it in a big way? Are we there yet in terms of technology, and what should we do? Is that an approach that should be pursued aggressively?
Thanks, Satya. So first of all, a big thanks to Satya for including me in this consortium. So I think it's a great event. I'm really enjoying it. Coming to biofuels, right? So biofuel is a very big term. So it includes a wide variety of fuels that we know about. It includes bioethanol at the least. And we know that we talked today about 1G ethanol, 2G ethanol, right? I mean, ethanol made out of food-based feedstocks, non-food-based feedstocks, which is 2G ethanol, right? And then biodiesel, and then drop-in biofuels, right? So there are different varieties of fuels that we can think about when we talk about biofuels. And then you have third generation biofuel, which is made out of, typically algae. So, so coming to where we stand in terms of, the biofuel production. So much is known. I would say that, the technological challenges aren't so much to crack. In fact, if you today look at 2G ethanol, right? So the India's target is to blend 20% renewable biofuel in the gasoline or petrol mix, right? And I mean, 2G ethanol is really talked about today, right? And what is the techno-economics of the 2G ethanol process, right? So if you really think about the cost of 2G ethanol, it turns out to be like 90 rupees per liter, right? And only if there is going to be some kind of a technology viability gap funding. Okay, so it's more like an incentive that the government gives just to make sure that the economic, even though the technology may be economic, right? But there are like a lot of challenges to really get to a scale. So unless that is done, right, it is not going to be really economical. So in fact, today in India, it is seen that 1G ethanol, which is made mostly out of molasses and other, partially food-based feedstocks, combined with CBG. That's the compressed biogas, is seen as a promising option. Okay. In fact, the cost of setting up, an equivalent scale of this 1G is going to be at least 5 times, smaller compared to the 2G process, right? And coming to algae fuels, right? I mean, in India, there are a lot of, demonstrations, success stories. We know that, Reliance did a massive, project in which they grew these microalgae in open raceway ponds and developed the technology to convert it to, the renewable fuels. But and there are also similar stories, in the south, right? We had Chennai Petroleum Corporation Limited, set up this huge algae farms. But the challenge again there seems to be the techno-economics. So why would I mean, this is something that I got to know by interacting with the refinery. So ultimately, the question comes to them that why should we really grow algae to really make the fuel, right? Whereas why don't you look at some feedstock that is readily available and that can be converted? Okay, so technology is there for algae, but today again by algae again there are 2 terms here. So one is the microalgae that has been widely researched, and now today with what is called as the Prime Minister's Matsya Sampada Yojana. Okay, so they are actually talking about growing seaweeds. So these are the macroalgae, and India with its broad, very large coastline. So there is a huge interest to actually multiply the production of the seaweeds. Okay, not only for fuel applications but also for a wide variety of bioproducts. Right. So these are this is the current status as far as the the third generation biofuels is concerned. But what I feel, okay, coming from so I've been working mostly in the biomass conversion area, and what I feel is we are actually missing to actually marry the environment with energy. I think that's the key. Right. So so much of what we talk about, the conventional fuels or the crude oil based fuels can be reasonably, compensated, okay, by the fuels that we can actually generate through pathways using solid waste as feedstock. So as long as we consider biomass as biomass, right? So we have a set of solutions, but you can always consider biomass and also other type of waste. And this is very much applicable in an Indian context because we have municipal solid waste, which is not just the biomass, but it does contain significant amount of waste plastics to whatnot. I mean, you can think of what is there in your dustbin, right? So there is a suite of technologies that are actually that can actually be employed to convert them to fuels. So think of it, right? So today, India is importing 80% of crude oil, right? And even if I'm going to actually blend, 1%, or if I'm able to generate through a technology just 1% of the the biofuel, or let me not call it biofuel, let me call it bio crude. Okay, it's not a fuel yet. Even if I'm able to mix 1%, that's going to lead to a significant savings in terms of the import, crude oil imports. So to sum it up, I would say that there are a lot of technologies. We know what the technologies are, but I think we are in a state that we need to actually identify the right feedstocks and then go ahead with it.
Thank you, Vinu. I mean, good to know that there are technologies, but I think there is a lot to do in terms of de-risking it to be taken up at a large scale. Now, I would like to call upon Professor Anuradha Ganesh to share some views on what are the big bets of OEMs such as Cummins. Transportation and engines are, of course, an important sector to decarbonize, and there are these sustainable alternative fuels. But the bandwagon seems to have been on hydrogen and electric vehicles. So, can you share with us some of your thoughts on what are the big bets of OEMs such as Cummins?
Thank you, Satya, for giving me this opportunity. Let me first talk as Anuradha Ganesh and not as a CTA of Cummins. Okay, let me just, I was just hearing everyone, so let me just put forward. I want you to look at a situation where there is an engine, there is an engine company which is going to develop. I look at it from a third person's view, all right? 3 years back, it was methanol economy. Let's develop an engine, convert the railway engines to methanol. All right. So the academicians also are all methanol, and the industry is being pushed. Why don't you convert a rail engine to methanol? Fine. And then the next year it is natural gas. All right. And then now it is hydrogen. Just imagine the state. Even if it was an academician, okay, a small engine in your lab, it becomes very, very difficult. All right. This you're talking about different fuels. Now I'll talk about the same fuel. All right. Vinu just talked about ethanol. I'll talk about biodiesel also. All right. We say 20% biodiesel. We still have only 6.6 or 5.6% biodiesel pan India. All right. So now I am an advisor to Cummins, and I tell them, listen, biodiesel, we should develop something because biodiesel is a diesel substitute. We are into diesel engines. All right. We are into commercial vehicles. So what happens? We develop for, okay, 20%, but what we are getting is only 5.6%. The engine performance goes for a 6er. All right, once it goes out. All right, then if we say, okay, let it be on, now they are selling B100. All right, so the fleet owners buy B100, they mix it, they are able to blend it, and they sell. And we have specifications for B10, B20. Very good. Now the fleet owner says, no, B30 is going to give me more, the value addition in terms of profit is more. So B30, and there my engine goes because now the material is not compatible. So I'm just giving you, these are a few things which happen where unless we don't have a clear roadmap, I agree that today we are in a middle mess, as we call it. We are, but I think still there has to be a roadmap. And I feel very strongly that this is a place where academia and industry can collaborate, work together, and give some informed choices or evidence-based decision help to the government. All right. Now, whether the government takes or not is a different thing, because we are today flex fuel, tomorrow something else, day after tomorrow something else. We want to run, which is very good. I tell you, believe it, the industries want to run. They want to run along with the academicians. It's only that one starts here and one starts here. You know, you're just not running together. All right. And there is a big gap which needs to be addressed. And that's where de-risking is a very, very important thing. I'll give you an example again. With all this, fossil fuels being there, and we know renewable energy is coming up, we also know, I would call hydrogen as a necessity. All right, because if we know storage, batteries are still, the technology is still being developed. Not that hydrogen technology is all ready, but yes, where the cost is more of a factor. So especially during those times where we need to use the solar energy, hydrogen becomes a necessity. All right. So that's, all that is there. But at that time, is it possible for us? Is it possible for us to have some, CO2 sequestration, which is very, very important for decarbonization? We not talked about it today. And that is not every small industry which will do it, unless you do have technologies now where you capture and you utilize CO2, but that's not enough. I know in Tuticorin and different places, I have seen some very good examples of CO2 capture and converting into soda and all, but that's how much can you do? So you have to sequester, right? Now, even if I want to, let's even talk about just capture. There are huge plants, there's huge investments, in 100 crores and above, 500 crores and above investment. Who's going to set up the pilot plant? Okay, you do expect some amount of de-risking to take place, but the de-risking of the investment, and that's where government has to, industry has to invest, industry will invest, provided it feels that some de-risking is being done by the government. That is one. In US, when they talk about setting targets, a beautiful program, Super Truck. I mean, that's my role model program. They have different industry consortiums reaching out to individual academia as and when required and as where required, and they are integrating to ensure that the targets set are achieved. What are the targets and who sets the targets? Now, the the overall engine system efficiency target is 55%. Can you believe it? 55% is a great target. How do we achieve it? There is one principal investigator industry which works with other industries, tire industry, bodybuilder industry, the engine, all of them put together. Okay, all of them work together and they achieve. So therefore, waste heat recovery comes in, air conditioning improvement, everything comes into that, and they have to together demonstrate a 55% target. And there are different consortium. It's not one industry and one set of industries. It is a competition, it's a bid. And there are different industries who are given the project, and they allow the technologies to evolve by itself. And there could be different competing technologies which are useful for different applications. We must have something like that. I think that is a very, very important thing. And that's where I think the TR level 6, or I would say 5 to 8, that gap which is there in the country today can be bridged if we have public-private partnerships, we have such super truck type of programs, and we have industry-led projects with academia supporting it, which is existing. Catapult, Fraunhofer, we have many, many examples for it. In fact, there are committees which are working on it. I think that's very important. And that I'm speaking as a person who has been in the academia as well as in the industry, and I really see the gap. Now, I did hear someone saying, and I'm myself very, very happy with IIT Bombay, IIT Madras research parks, even IIT Ropur, there's so many doing it. That's not enough. That's just not enough. We really need more. We can't have just IIT Madras and IIT Bombay and IIT Kanpur and IIT Delhi doing it. We really we have to bring in our tier 2 universities also. We just can't have 5 of them running the country. It's not possible. Let's understand that. Whereas I do agree that IIT Madras, I myself have connected with them, and I myself have taken technologies for comments from there. But I have taken from IIT Bombay, I've taken from IIT Delhi in the capacity of Chief Technical Advisor. But I do feel that there are many more who are left out, and I think they should. And we really expect the academia to raise to that level and help the industries, because you really need to reach out. Now, whether it is industries to reach out or the academia to reach out is something which we can work out later. And I think I'll stop here. There's a lot that I can speak, but I'm going to stop here.
Thank you, Professor Anuradha. I think that really sets up a couple of questions. You talked about the frequent changes in goalposts or milestones. You talked about choices. You talked about de-risking. So now my question, this is for Professor Deepak, is, are there holistic frameworks that we can employ a priori to analyze this transformation. For example, a lot of us in the previous panels discussed KW is not KWH. It's misleading to just only talk about renewable addition. I'd also like to add here, KW added by way of renewable is not KW replaced. So are we really replacing the baseload capacity? Because there is also interruptions and there is also a non-availability infirmities. So what are the frameworks that you know that could be used? And maybe you can comment on, are they adequate? Are there things that we can learn and deploy from some other areas or new frameworks that could be developed to really analyze this transformation and set up the roadmaps that Professor Anuradha really talked about? Deepa?
Yes. Can you hear me?
Yeah, we can.
Thank you.
Yeah.
Yeah. Okay. So thank you, Satya, for that. Again, thanks for the invitation to be here. And also thanks for the option to participate remotely. Apologies for not being able to be there. And yeah, it's an honor to be here. Just one point of clarification. When Satya introduced me, it's perfect. I was an engineer for 10 years after leaving IIT, then for 10 years I was an economist. Now I'm not an activist as much as a skeptic. I mean, activists will take offense at me because if they hear that, I'm not. I do work a lot on biofuels. I did a lot of work on biofuels. I did a lot of work on electric vehicles, and I'm doing it, but I'm really not a champion for those. And what I want to talk here is this being a largely an engineering focused audience, and business folks. And since I am part of a department at UCLA, which is interdisciplinary, because one of the things about is the institutional innovation we want to talk about that Dr. Ganesh spoke about, or I'm part of a department where I'm one of 13 or 14 faculty, and each faculty is from a different disciplinary training. We have lawyers, we have biologists, atmospheric scientists, and one person from every department with a joint appointment with another department. I have a joint appointment with urban planning. I'm sort of more of the engineer person, but I don't do that much engineering. But what has been fantastic is working with people from different disciplines, even within an academic setting. So I want to take a sort of a non-engineering perspective, bring a non-engineering perspective, and also, yeah, you rightly said, I speak about the policy aspects. So that's what I want to touch upon. And the work I do is methodologically the framework I use to analyze energy systems in a more holistic sense is called life cycle assessment. Essentially, looking at technologies or products or services, not just what it takes to make them or what pollution happens at the point of use, but the entire supply chain, right from wells to wheels, or right from the farm to the end of life. And so that's like a life cycle assessment perspective, and you look at it, and essentially it helps you identify unintended consequences where you might have pollution shifting. We had Professor Venu speak about biofuels. I've done work on that as well. We heard about hydrogen yesterday, but if you see about hydrogen, one of the things is it takes about 10 to 25 liters of water per kg of hydrogen, right? Stoichiometrically, it's 10, so you can never go to get better than 10. So, and realistically, you're probably going to end up with 25 liters of hydrogen, water per hydrogen, right? And so it's not, and I know the focus is on carbon and climate change, and everybody talks about climate change, but life cycle assessment tells you there are other things that matter. It's not just about carbon. If you look at the Indian context, air pollution is extremely important. Water is extremely important. So one of the frameworks I think we really need to use as a starting point, I would think, is life cycle assessment. It's a very nice framework for engineers to start off because it's very analytical, it's very quantitative. It's about mass balance, energy flows, doing it very systematically, but that's just a starting point. So I would start with the life cycle assessment perspective, look at technologies, but then not really stop there, because I think one of the key messages I want to say here is that the benefit of a technology, the social benefit of a technology, is not really a function of its own footprint. It's not really what it takes to make. Otherwise, then we will say the best technology is like, so let's give you an example, right? You can make a product very clean with your own, and try to do it with renewables and so on. But when you scale it up, you're going to draw resources from the rest of the economy, right? I mean, so essentially, when you scale it up, it's going to, so biofuels, for example, you can grow biofuels, even first generation biofuels can be made very clean. You don't touch forests. You just use degraded farmland. You grow stuff, but then you need to grow it with some, if it's degraded land, you need a lot of inputs, fossil inputs, fertilizers, and so on. You transport it. And then let's say, oh, I'm not going to use fertilizer. I'm going to do it organically with animal manure. I'm going to transport it with clean trucks, and then I'm going to convert it with clean energy and have a zero carbon footprint. But that is not really scalable. If you scale it up at some point, you're going to start eating into farmland. When you eat into farmland, you're going to displace food. When you displace food, you raise food prices. When you raise food prices, farmers will go convert forests. So that's going to lead to, so you, and Vipul, I think mentioned earlier about scale, and let's come back to scale. So the real social benefit of a technology depends on what is its footprint when it's done at scale. And when it's done at scale, engineers talk of driving down their own footprint because of learning by doing. Sriram mentioned very important concepts of learning by doing, which actually helps the engineering part of the curve, right? You drive down, your own supply chain becomes more efficient, but you have unintended consequences in the rest of the economy, what economists will call general equilibrium effects. Or you draw labor from other resource places, you draw land, you draw materials, and that can actually hurt you, which is essentially the problem with scaling up biofuels sometimes, right? So, or scaling up with hydrogen, we're going to take up a lot of water. So that's so first point, we need to take a life cycle assessment perspective, but that's just a starting point. We really need to look at the social footprint of a technology, social benefit of a technology, which extends far beyond its own supply chain. Just give one more example of energy efficiency, right? From an engineer's perspective, the more energy efficiency, the better. Absolutely, because for us engineers, energy efficiency is a ratio, output over input. From an economic perspective, efficiency is not a ratio. Efficiency is output minus inputs. Right? That's where the marginal things come. It's not a ratio from an economic perspective. For an engineer, it's always a ratio. That's a very fundamental, it took me a long time to understand, but it's a really important point, right? That's why economists' efficiency is benefits minus costs. It's not benefits over costs. And so sometimes, so that we need to keep that in mind. Sometimes too much efficiency can be a bad thing because it just costs us too much. You can't just keep on increasing efficiency. Sometimes we have to be inefficient because in a system-wide sense, that inefficiency frees up resources for something else. So we need to take a more holistic perspective. And so this is what I want to say is, we really need a research agenda, which is not, I know we are an engineering institution, that's our core strength. But I think we really need to undertake serious interdisciplinary research and not just do lip service to social science. I know I have engineers come and tell me, oh, for an engineer, economics is all about doing cost budgeting. I mean, that couldn't be farther from the truth, right? And again, it's about really understanding how constraints and resource constraints, general equilibrium effects all matter when you scale things up. And you take it further, it's not even just about economics. And I know engineers and economists dominate the debate, but it's not even about engineering and economics. It's actually a lot more than that. We need a real perspective on energy transitions. If you look at all the energy transitions in the last 150 years, something is strikingly common to all of them. Every one of them, if you went from animal power or water wheels or wood to coal and steam engine, and then from coal and steam engine to oil, and then from oil to gas, and then or from heat to electricity, every one of them has been about a transition to a better energy resource, lower cost per unit, more convenient, less labor intensive, and so on. The transition we are attempting now is fundamentally different. It's not about a better energy resource. Hydrogen is not better than oil in the sense that hydrogen is best for, because it's an energy storage device. Electrons from solar are no better than electrons from burning natural gas, right? I mean, these are really not better energy resources. So we have to work much more harder, because what we desire for is clean energy, not a better energy resource. To some extent, going to electricity will help, because it can help with a lot of mechanical work more efficiently. But fundamentally, we have to be realistic that we are seeking not a better energy source in terms of its better energy quality. It's just cleaner. We want something cleaner. So, and there is a lot of fantastic research by geographers and historians of energy talking about how long energy transitions take. They've looked at coal, oil, gas, and for everything, it's like a S curve, but S curve, like, it's like, it takes about, just to get to 25% of the energy market share takes 50 years. And what are we talking here? We're talking about throwing away 90% of our fossil fuels in 20 years. So I think we just need to have some, so again, that's why I'm saying if there's any doubt that I'm an activist, this should clear it. But I'm just saying this doesn't mean we don't do it. I'm just saying we just have a little bit more, we need to take we need a broader perspective. We need history. We need a historical perspective. We need a geographic perspective. We need a social science perspective. And let me just conclude with a couple of things on the policy stuff. So that's on the research side. As a research initiative, I hope to see that the IIT Madras Consortium collaborates with, just as it collaborates wonderfully with business folks. We bring in folks from social sciences. I for one myself did not take my humanities electives in IITM very seriously. It was just some coursework, but I really realized the value of social science education now. So that's on the research side. As on the policy, I think we really need policy experiments. I think as engineers and scientists, we talk of scientific experiments. We need policy experiments. And we need to experiment with what types of policy. So one example in California, I mean, US is, I have to be very careful of advising about policy sitting in the US, but one in California, we had a really cool policy that I have studied, we worked on. One is called the low carbon fuel standard. Essentially, it's a life cycle based standard. Traditionally, when we try to regulate pollution, we regulate pollution from tailpipes or just from smokestacks. This is a policy that sets standards on life cycle emissions. And so you try to reduce pollution on the entire life cycle. And so it's a tradable policy, there's incentives and rebates and stuff. So we need to think of having subsidies. So we need to do taxes, carbon taxes, and all those nice sounding stuff. We need to have subsidies, but we also need policy innovations, low carbon fuel standards, life cycle based emission standards, institutional innovations. The Solar Energy Corporation of India is an institutional innovation that came about that is actually driving down the cost of solar, that is helping guarantee payments for investments made by small investors, that you cannot rely on governments on their whims and fancies rewriting contracts. We need institutional innovation. Professor Ganesh mentioned a wonderful innovation that's happening and about the US, in the US, about the industry consortium, like the DOE Super Truck program. I've studied it. It's fantastic. It's actually led by by industry, but has a very strong academic contribution. Now they're also trying to have a community presence, community participation. I was actually asked to evaluate their diversity and inclusion criteria. And I said that, it was exciting to see that they're bringing in community stakeholders right early on, because trucks hurt communities a lot, poor communities a lot. They inhale most of the pollution. So we need institutional innovation, policy innovation, research innovation, not just technological innovation would be the point I will stop with.
Sure. Thank you. Thank you very much, Deepak. I think a lot of us skipped history and probably did not or slept through history or whatever humanities courses. But nevertheless, we are learning it. It's never too late. Now, before I open these panels for question, I just want to maybe quick word from Professor Muruganandam. I know he is not feeling well, so I don't want to trouble him too much. But while there is so much more to do besides just technology, I just want to get a sense of readiness of technology for utilizing hydrogen. You work on gas turbines. So how ready are we? Are we likely to see power generation or aviation pick up hydrogen-based engines? And is there something India is likely to play in this roadmap? Muruganandam?
Hello, everyone. Can you guys hear me?
Yeah, we can.
Somehow video went off.
We can hear you well, Murugan.
Okay, somehow video is not working right now. But anyways, I'll start by saying that we are already working with GE on a gas turbine center where we are working on developing fuel flexible gas turbine engines. Along with that, there is another startup company called Aerostravillos. I believe Mr. Vipul Tuli would have visited NCCRD today, so he would have seen that as well. Aerostravillos is a startup company which is coming out of NCCRD based on one of the patents that I'm also part of. They have licensed the patent and they are working on developing small gas turbine engines which are again going to be fuel flexible. So it can work on biofuel, it can work on methane. I believe they've used methane plus hydrogen mix and it worked, and it is working for several fuels. So whatever be the blend you given, it seems to work. Okay, and it is being used for power generation. They are also contacting electrical professors. I believe Krishna Vasudevan was also in that team. So they are getting into the microgrid business, and they are saying that I will give it to one set of apartments together, something like that. They are generating something of the order of 100 kilowatts. So these kind of small grids definitely can work with hydrogen in the short term. If you're thinking long term, say power generation by big gas turbine engines, that's, I think the gas turbine industry is such a big industry with so many restrictions for operation and checking and all that. I think it'll take 20 years to make any change. It has huge inertia. Nothing can be done about it. But I'll tell you that most of the companies are having a race to demonstrate their very first renewable fuel, which it's going to be a mix of LNG and hydrogen. They are trying to get alternate fuels other than SAF, okay? Sustainable aviation fuel, another form of some liquid fuel. So compared to that, they're trying to have a gaseous fuel gas turbine engine by 2035. That's the race they're all running towards. And we are working with GE on that, while other engine companies are all working with other major institutions of India, like IIT Kanpur, IIT Bombay, IISc. Okay, all these places are working with different companies. Okay, and GE is big time into IIT Madras, and they are also working with IIT Kanpur a little bit. Yeah. Okay.
Thank you very much, Mugi, for that quick intro. So now that we've heard a couple of things, right? Technology is evolving, hydrogen or biofuels or many things are evolving, but we still need to get into decarbonization. In all of this, we heard a lot about de-risking and probably clarity of vision, and an example was given about SECI. So maybe I'll open up this panel for questions. So if any of the panelists out here would like to discuss something more about what we heard till now, before we open up for the questions from the audience.
So Satya, if you would allow me to answer one comment which has been written here.
Sure.
Someone has written that today young in academia is very keen to work with industry. Visit us sometime at IIT Madras Research Park. I have visited many times. I have also picked and worked with some of the industries there. You will change your mind. I don't know what mind I have to change, but nevertheless, let government not tell us what to do, but government has already given the mandate. So there's no question of telling us what to do. The mandate is there in front of the whole world. The industry and academia should put out a program and government should support. That's exactly what I said. The way industry runs after government, they should instead work with academia. Unfortunately, the regulations and the policy incentives come from the government and not from the academia. So it has to be a tri-party collaboration. Please remember, we cannot leave out any one of them. Academia is a very, very important part of any industrial development, but at the same time, we have to go hand in hand with the government policies. Yes, The academia and the industry together, the industry bodies, feed the government to help them make informed choices. And I repeat that. I think that's very, very important. Government is a set of people there who are looking for information. Otherwise, they can't make the policies and they can't make any regulations. It's all based on the evidence and data that we provide together, academia and industry. I hope that answers your question.
Thank you, Prof. Anuradha.
I'd like to make a couple of comments, if I may, Satya.
Sure.
I think one is about, just to pick up from what Ms. Ganesh said. If you're a young person in technology or engineering today, I couldn't think of a better time to be in this era of human activity. Couldn't be a better time. And I'll tell you why. I'll give you a very specific renewable energy reason for this. Okay, if I look at India, the renewable energy expansion or explosion that has happened and is continuing to happen at the moment in most of its forms has basically not been technology driven, at least for India. It's basically been management driven. It has been driven through management innovation, through finding the best capital, scaling up bigger projects, faster execution, matching technology with sites, etc., better operations, more digitization. Okay, digitization, you're now venturing a little bit into technology. Okay, fine. But basically, it's been management innovation. To my mind, from where I sit, I think the era of that management innovation is giving way to a new era of technology innovation. Because I think we are getting to marginal returns on the management innovation. Not that there won't be management innovation, but technology has surprised. It hasn't been too much of Indian technology yet. That era is now starting, and the next wave, whether it's storage, batteries or hydrogen or something else, and some of the others that I mentioned. So in that sense, this is the time for energy, technology, innovation in India, and this audience, or those whether in the room or online or whatever, this is your time. The next 2-3 decades is your time. That's point number one. Point number two, I just want to make a comment on the policy side. I think many people referred to it obliquely, but maybe I'd like to volunteer sort of 4 things that I feel policy in India has to address to be able to get this tech transition right. Some of these are obvious pain points and some of these are less. One is, I think, viability funding for transition solutions, which will typically be more expensive to start with. Where the technology is very well known, I can do it, but unless I scale, etc. So viability funding for transition solutions. I think number 2, facilitation and incentivization to pilot new solutions. Whether it's the hydrothermal liquefaction type of stuff, or it's some new coal plus biomass gasification or something else, not just incentivization financially, which is relatively easier to do, but the facilitation of how do you get this stuff set up and absorbed into the grid, number 2. I think number 3, just ensuring bankability of institutions in the sector across the chain, okay, which does not exist today. I won't repeat what I said earlier. And number 4, I would say, I think the government has done a lot to help source the right type of capital for the right type of risk. A lot has been done, but there are still many obstacles, many frictional costs or restrictions for the right capital to come in. I mean, if you want really low cost, long-term infrastructure capital, then your yield funds, etc., just need to be completely seamless. Your tax rates just need to be more competitive than anything else in the world. However, if you want much more venture capital or technology risk capital, you need to find a way to get that in. So the policies that allow capital to come in and address the right. So these 4 things, I think, on policy. Lot has been done, lot more needs to be done.
Thank you, Vipul. That really sets the context for my next question that I want to ask. I mean, this is open to all the panelists. Is We talked about SECI's example. Deepak mentioned that SECI has really helped the solar projects take off in India. Are there any other such examples that you think will help the rest of the transition to 2070 or 2050 or 2047 that we have agreed in the summit? But nevertheless, what kind of institutions needs to be set up to really achieve that?
Can I go ahead, Satya?
Yeah, please.
Okay. So, so if you really look at the variety of technologies that we have for, be it for hydrogen or renewable fuels, liquid fuels, right? So, so as I said, right, in my response to your question, there are a wide variety of technologies, but I think we are really facing, we are not really able to demonstrate at a scale, right? So only those technologies. So we go through a typical techno-economic evaluation, right? And of course, every technology has a scale at which it is going to be, winning. But it is important that we have, as rightly also pointed out in one of the other sessions, it is important that we need to have, a government, a private, and a public partnership. I think that's the key to it. And this also needs to have, a substantial, government funding or something like a viability gap funding from the government to really demonstrate the technologies at scale. So today, considering IIT Madras or the Combustion Center where we are from, so we are not really working at scales that once typical academics would do, that is a bench scale. So we are really demonstrating at scales, which are which is something that the industry can easily adapt. So, for example, if you ask me what is the scale at which we work, so for example, we work on a hydrothermal liquefaction process, and we are easily pitching something like 5 tons per day of municipal solid waste processing to biofuels, right? So I would say that even we as academia, we are really capable of demonstrating at reasonably larger scales, and we really look for, of course, an industry partner. I mean, at IIT Madras, we do have a good set of industry partners to do it, and I think we also need the required government support that would really help us progress.
Thank you. So, yes, government support, institutional support is needed, but I think there is a lot of de-risking. We heard the word de-risking so many times. I think there is also this element of technology de-risking and then maybe financial project viability de-risking before things could take off. This, of course, a continuing debate, and that's the point that we want to address to the consortium. So before I close, maybe I would like to open up if there are any questions from the audience. I know there are quite a few online, but let me take Deepak. Yeah.
Oh, just wanted to add to that in terms on the de-risking part. One of the other mechanisms of de-risking is also guaranteed demand that drives investment, right? I mean, so essentially, if the private investor can see that in addition to, like, of course, financial guarantees are there, but there should be guaranteed demand that is driving the actually procurement. So industries may not like it, but at some level, you need a certain level of mandates. So a mandate for not an insane amount, because we don't want to mandate 100% or mandate 50%, but mandating 10 or 20% and saying that, the dirtier people are obligated to mandate cleaner fuel, just like you have with biofuel. The only question is, when the government itself is the main supplier or the distributor, how effective are the mandates? If it's a private sector, actually, that's in the US, where it's like delivering the fuels or energy, the mandate can work. So mandate sends a clear signal that if it's going to be enforced and if they have to procure, and so you back the subsidies with mandates, because subsidies without mandates, there's very clear economic reasons why subsidies without mandates are not as effective. So when you couple the subsidies with mandates and you couple that with life cycle based standards, then it also creates some competition for people to come up with the least carbon intensive or the least pollution intensive, and the subsidies go much farther. So
I think
that's
that's
what the policy innovation is. Yeah.
I think creating demand probably by mandating converting to LED, or at least promoting LED through what do you call low cost schemes, and maybe guaranteed offtake agreements that came up with the SECI. I don't know what's going to be the mandate that will drive the rest of the innovation that is required, but I think this is a debate that will probably continue. Maybe I'll open this up for some questions. We have one question.
Can I ask question, or am I audible? I'm Professor Jhunjhunwala.
Yeah, yes, Professor Jhunjhunwala.
Yeah, I wanted to ask a question. There was talk on this biofuel. Do you have some understanding of how much does a kilowatt hour of electricity generated from biofuel will cost today in India?
Okay, so this is Vinu, Professor Jhunjhunwala. So today, if you take a biomass such as rice straw, which we all know is a key biomass from the Punjab. The power, the biomass power that you generate from it is at least 2.5 to 3 times as costly as solar. So the biopower isn't really cheap as compared to solar. And so in a recent report that we submitted to the Niti Aayog, we basically recommended that biomass to power isn't really the right option to go with, but we should probably be looking at even intermediate things like steam. In fact, if you compare the cost of steam from coal, the paddy straw based steam generation at an equivalent pressure and temperature is going to be at least twice as cheap.
Can I respond to that also?
Yeah, sure.
Yeah. So just from a life cycle based calculations or life cycle cost calculations, if you look at it, there is very, very little economic case for actually using biomass for electricity, simply because you have much better uses for it. If you spend a little bit more money, you can get a much more value added product. So yes, burning for biomass is simple technologically, but because it's competing with very low cost alternative resources, if you spend a little bit more money and upgrade it to a better product, you actually derive a lot more value addition from it. So I mean, so there is, in very few places is there a strong economic case for burning biomass for electricity. You would much rather make something more value added out of it.
Deepak, what about bio waste to electricity?
Yeah, bio waste to electricity. Yeah, we looked at it. We published a paper in Nature Energy a couple of years back, looking at bio waste to electricity. There are some, if you don't have huge transportation costs, again, there are niche applications where you can use it. Even there, we saw that if you want to maximize environmental benefits, you probably have to do something costlier to burn it more cleanly. But if you just want to burn it, it's cheaper to do it. But again, it has to be those situations where you really don't have the electricity from the grid. So it is, again, goes back to what are the every technology has a niche. I'm sure burning biomass to electricity has an application. We just need to find those use cases, which would be where you don't have access to grid or access to cheaper alternatives. So I think that's the thing there. It's not that it's universally not economical or universally not uneconomical.
Yeah. Professor, I think Vipul here, I think that's a killer question. Okay. I don't think I have a clear answer. But and I agree with Deepak that there are different use cases. Okay, I think there is the simple calculation of firing it in a conventional boiler. If you look at, of course, prices vary, etc., but it's roughly, the variable cost is roughly 3 times. So if you have a 2.5 rupee variable cost, it becomes about, well, close to 3 times, 6.5, 7 rupees. Okay, so clearly, if you so what that means is 2 or 3 interesting implications. One is, I think the comparison with solar, of course, as Vinu said, it's more expensive, but this is dispatchable power. Whereas solar without storage is non-dispatchable power. So you're talking very different products, very different use cases. Maybe it'll work. Maybe if you can get it down to $5, maybe you do. Related question becomes, if you're growing biomass for this, are you really decarbonizing? If you're using waste, maybe you are decarbonizing. If you then come back and say, I also tend to agree with Deepak that if you have alternate uses from, say, gasification or some form of liquefaction of the waste into higher value end products, then pure power generation is not a great case. But here we are, yet we have a mandatory 5% by October 2022 to be fired in all thermal plants. So I think I haven't answered your question, but maybe at least explain why I think it's a killer question.
I think, thank you very much, Vipul and Professor Junjunwala, for that question. We're almost out of time. So the theme that's really coming out is our ability to provide technology and evidence-based support to the government in actually decision making. So we do get mandates, probably which does not make sense. We do have opportunities where there could be a lot of potential, but we don't have mandates, so we don't develop technology or we don't scale technology. I think there are 2 great themes that's coming out. One is de-risking involves providing some way of support for academia, for industry, for joint product development, for clarity of vision, roadmap development, and also as academia and maybe the consortium to provide technology and evidence-based support to the government in decision making. Well, I would like to thank everyone who participated in this session. Thank you very much. We don't have any more time for more questions, but we wish you had a great time, and we hope that we will continue this engagement and really get to some of these problems and questions. Thank you, everyone.
Thank you.
Thank you.
Thank you.
And very nice meeting all the panelists too, co-panelists. Thank you.
Yeah, thank you all.
Thank you very
Nice to
much.
meet you guys.
Thank you. Same here.
Thank you, professors, for such a wonderful panel session. May I now request Professor Raghu to give away mementos to our panel members. To Mr. Vipul Tuli. To Professor R. Vinu. Professor Satya Sheshadri, one of the hero of the entire show. May I call upon the other heroes, Professor Rajneesh Kumar. Professor Preeti Agalyam. Arvind. Professor Arvind Kumar Chandran. All your students. And we have Professor Swapna Singha Rabha. We also got a wonderful support from the Australian consulate and the US consulate to Miss Amy from Australian consulate. To Mr. DJ Meeks from the US consulate. Thank you very much, Professor Raghu. May I now request Mr. Sanjeeva De Silva from the Australian High Commission, New Delhi, who is the Councillor for Industry, Science, Energy and Resources. Over to you, sir.
Thank you very much, and thank you for the invitation to speak. Can I just check that I'm audible and being heard? All good?
Yes.
We can, sir.
So thank you so much for having me, and I hope that someone has my presentation is able to navigate through it. Will they put up my presentation? So thank you so much to IIT Madras for having me. And today I want to just take you through the journey that the Australian government went through over the last 3 years in addressing really the fundamental question of all of these technologies that we've been hearing about in the last session, of all the many options and pathways that countries have towards lowering their emissions, towards the prosperity and the jobs that we try to access through whether it's the hydrogen industry or electrifying various processes. How do we understand these technologies? How do governments select and choose which of those technologies to champion? And then finally, how do we then partner internationally in order to make those bring those technologies into cost competitiveness and broad deployment? If I can move to the next slide. About 3 years ago, in August of 2019, our Minister for Energy asked me and a small team in the Australian government to think about what our vision, the Australian government's vision for technology deployment in the low emissions tech space was, and how that would translate into priorities, clear and present priorities into 2030 and out into 2050. And in doing that, I had the great luxury of being able to talk to some of the most eminent scientists and businessmen in Australia in order to get their views on how we would build this vision and help the minister in developing this roadmap that he wanted. And one of those people was Dr. Alan Finkel, and he was the chief scientist at the time, and he was very fond of this quote by Buckminster Fuller, which says that you never change things by fighting the existing reality, but rather you change things by building new models that make the existing reality obsolete. And that was really one of the guiding sentiments that we had, that we, as the Australian government, weren't going to go about dismantling parts of our industry that were perhaps carbon intensive or trade exposed. We were going to embark on a process of really building a new model for the future that would then have such a compelling case for consumers and people who are users of electricity or green steel or whatever, that such a compelling case would be built that that new model would come into fruition. Can we go on to the next slide? Now, the first thing I realized when I was designing our initial briefing for the minister on how we would do this was that it is a very, very complex area. In fact, the team of sort of scientists that were advising me at the time identified in very, very short time more than 150 technologies that we would need to look at very seriously before we were able to pick just a few that we could in the near term support. And I want to just firstly focus on that idea in the first instance. One of the great things about working with scientists, and I'm sure I've only just arrived in India, but I'm sure it's very, very much the same here. One of the great things is that every scientist and professor that you speak to, who's a technologist, who's an engineer, or has been working on a particular technology, they will advocate for their technology. It is as though it is the only one that is in the whole world, and that is the answer to all of our problems. But when you start listening to many of these groups, it becomes very clear that as a government, you do need to have an ordered way of understanding which technologies you're going to prioritize. And then you have to understand that you probably will get that prioritization wrong year on year. So you have to adapt and be open to new technologies as they come along. So what we did was we got advisors and consultants to help us to develop a sort of very clear, logical matrix by which we would, as the Australian government, iterate through developing these priority technologies and surveying which technologies were out there in order to work towards a vision. And this was the schematic and is the schematic that we now work to in Australia. And the reason that it's important in this context of international partnerships is this is the framework that Australia will be using to select the priorities that we will be supporting in the low emissions tech space. And this is the sort of schematic that we will like our partners to also help us in developing. And I'd like to quickly just run through this. The first, of course, before a government embarks on any kind of partnership or any kind of funding, has to be very clear what its vision is. Where is it trying to get to and by when? The second thing we decided to do was that we would survey, do a quick, fairly high-level survey of all of the new and emerging technologies that were available to us in trying to decarbonize our economy. And as I said earlier, we had a team of about 16 scientists and engineers and policymakers working in my task force, but we had a much larger team of people that we were consulting and working with to survey these 150 technologies. And they ranged from everything from small modular reactors to heat pumps. That was a very popular one in the building sector, to very new heat pumps, to green steel and green aluminium, DRI technologies, all the way to livestock feed supplements, the whole gamut. So we looked across our entire economy and we asked experts in each of those sectors to identify the technologies that they thought had capacity to deliver large emission reductions. Next, we went about asking the question, what is Australia good at? What are our comparative advantages? And what gaps do we have that we would, what special and unique needs we have as a country that we need to look for ways to bring in technology from outside in order to fill. Now, this is a really interesting stage of this analysis when you start thinking about partnership. And indeed, Australia's Prime Minister, when he met with Prime Minister Modi not long ago, said that we would embark on developing a partnership with India. And indeed, one of the things that we are trying to do is to understand in detail what Australia's comparative advantages are. On the other hand, what India's comparative advantages and strengths are, including in the space of research and development, and where those two things kind of come together to suggest that the two countries can have a meaningful partnership. So in this space, we of course went out to industry and others, and what we found was, of course, that Australia is very strong in very discrete areas of research and development. For example, Australian PERC technology and solar research has long been world leading, and in fact, quite recently, a small team of researchers from the University of New South Wales broke the world record for efficiency of solar modules, and in a similar way, Australia had developed PERC technology, which is now in more than 80 or 90% of all solar modules in the world, including an Australian Australian technology. So solar was one, but others include, for example, carbon capture and storage, because Australia has invested over many years in that technology. And so we've developed research and development strengths in that area. So like that, we developed a list of all of the research and development strengths we had, but we also looked at things that are inherent to our economy, like, for example, the fact that we have a very large land mass with a lot of sun, a lot of wind. So it suggests that Australia can deploy renewables in a large way. If you'd like to read more about it, I can send you some links of some of the work that we've done back then. After identifying Australia's comparative strengths and our needs, we went through a process of prioritization. And to do this, we engaged the help of a panel of eminent Australians, including the head of Macquarie Bank, Shamara Vikramanayake, our chief scientist, Alan Finkel, but various other people who had a lot of strength in understanding different sectors of our economy. And my team then developed a lot of analytical work to help that panel advise the minister on which technologies they thought would have the biggest impact on Australia. And we looked very deeply at a fair few of those. Now, from there, I'm going to sort of race through this chart, but I wanted to convey the idea that Australia goes through this process now year on year. So we've just released our second technology statement, and that again, it surveys all of the technologies that we had. It updates the survey that we had done previously. It adds to the priorities that we've developed, and it runs through this same schematic to ensure that Australia is staying on top of the most recent technological developments. Can I move to the next slide, please? Now, I mentioned a vision, and this was actually one of the most interesting discussions I've had as a policymaker, was talking with that panel about how we condense what we're trying to achieve into a very, very simple idea. And what came out was that in Australia, what we are trying to do is to become a global leader in select low emissions technologies. And that global leadership will, of course, result in lower emissions, as we deploy these technologies. It will result in prosperity for Australia, but really at its core, what Australia is trying to do and what we're trying to do with the international partnerships that we are developing is we are trying to lead the world in select low emissions technologies. And what exactly does leadership mean in that context? Well, leadership is more than just the technological breakthrough. There's famous examples in the Australian system, I won't go into them, of where Australian innovators have come up with fantastic intellectual property, fantastic ideas, but then have gone offshore in order to promote them. That for me is part of, making the scientific breakthrough is part of being a low emissions tech leader, but it's not all of the story. I would like to see Australia with the countries that are partners with, including India, not just come up with the new breakthrough technology, but then see that technology through to commercialization and towards globally competitive new export opportunities. That, for me, is really the heart of technological leadership. If I can go to the next slide. Now, I've spoken a lot to these ones already, so if we can go forward another slide, please. Now, in terms of what technologies we chose through that process that I've just described, and how we came up with, or how our minister wanted to see these technologies deployed. One way to try and deploy technologies, low emissions technologies, once they're developed, is to increase the cost of existing high emissions technologies. So, for example, by taxing existing coal-fired power or existing fossil fuel generation. That's one pathway towards trying to encourage low emissions technologies. The other pathway is to try and provide support, encourage deployment and innovation in these low emissions technologies to bring their costs down so that they are cost competitive with the existing technologies. And that was the approach that Australia really wants to embark on. So one thing that our team did was, at the request of the minister, was that we looked at, through the process that I described earlier, the panel, along with our analytical experts and the minister, we came up with this list of 5 technologies. And you'll see that there's 6 there because one was added after my time. But we came up with 5 initial technologies plus ultra low cost solar, which was added this year. But this is from the list of over 160 or 70 technologies by the time the survey had run. We looked at these and we assessed which had the greatest potential to deliver emission abatement, where the technologies were at. So all of those things together, we narrowed the list down to this 6, and I'll quickly go through them. But we identified the cost point at which these technologies would become cost competitive with existing higher emissions alternatives. So for example, clean hydrogen production at $2 per kilogram. At that price, clean hydrogen would become cost competitive with natural gas in a number of applications. For example, our analysis showed that at $2 per kilogram, hydrogen would be cost competitive in heavy vehicles, for example. Perhaps in some gas blending, it would become cost competitive. Perhaps not across the board, but in certain niche applications, a demand stream would flow from $2 per kilogram hydrogen. If we take another one of electricity from storage, now that's a really interesting one, and I would love to hear from other panelists and people in the audience as to how this would measure up in India. But at $100 per megawatt hour, now this is talking not about the end user electricity, but rather the cost that is paid by, for example, an electricity retailer for dispatchable energy from stored electrons in its stack of electricity that it then offers to the consumer. So for example, you might be paying $100 per megawatt hour for a given percentage of your mix, but you would also be getting very low cost solar and wind at particular times in the day. But this was the amount that would allow you to firm the electricity from intermittent sources. And so we identified $100. In that same way, we identified cost points at which, if we could get the technology to that level, it would become broadly deployed, not through any further government action, but simply by the fact that it was cost competitive with existing technologies. I'm not sure by my count, I have a couple of minutes left, so I might just skip forward a slide or two. Can I see my next slide, please? So this is, where the financial commitment that the Australian government is making. And by 2030, at least $20 billion will be put into these technologies that we are prioritizing. It's important to note that while we decided it was very important for us to prioritize a small group of technologies because we can't do everything, it was important that each year, through that same process of surveying new developments in technology, we would leave ourselves open to the idea of both adding new technologies, but also taking existing technologies on that list off if they were not performing. So at least $20 billion will be allocated by 2030 to this list of technologies. And with that money, we hope that to drive the innovation, but also drive the commercialization of these technologies. Now, in amongst that $20 billion, it's actually 500 or $500 million that has been allocated to develop our international partnerships. And those international partnerships are being driven by our former chief scientist, who I mentioned, Dr. Finkel. And so Dr. Finkel has been in touch with colleagues in India. We are very close to concluding a partnership with India, and Dr. Finkel will be really interested to meet scientists across India in the future to look at where we can develop these technology partnerships together. If I can just skip forward again. Now, this was some fledgling thinking that me and my team, Radhika Tumar and Shandon Atreya, we have been in India just thinking about how India's comparative advantages and Australia's might intersect and complement each other. And this is in a very particular example, in the context of battery manufacture. And as you would know, the Indian government had very high ambitions on the deployment of renewable energy, but it also has very high ambitions in terms of manufacture of batteries and the batteries, adding value to batteries supply here within India. Now, while that's a very strong ambition, these supply chains move very, very quickly and evolve very quickly. So if we look at lithium batteries, we don't really have that long before new technologies, maybe in 20 years' time, might have already displaced some of these technologies. So if we want to make a globally competitive offering, we need to move very quickly. And what Australia and India are now trying to do is to add value in each of our countries, but then partner to bring those offerings to market more quickly. And as a basic schematic, Australia is very strong in terms of its mining sector. We have excellent upstream infrastructure in, for example, critical minerals and other things. India at the moment is manufacturing batteries, but largely through imported components. But what we can see and what we are looking forward to in terms of a vision is that Australia and India can both add more value to meet in the middle of this supply chain, so that we can bring more value-added products to the market. And this same schematic, in my mind, applies in a variety of other sectors. I don't want to overstretch my time, so I might just leave it there and hand it back to the organizers, and I'm very, very happy to answer questions. Thank you.
Thank you, sir. Thank you for your talk on imagining partnership for energy transitions, the role of technology and policy cooperation, and it was really amazing. We would really love to honor you with a memento. We will make it to reach you through a post, and may I request Professor Raghunathan Rangasamy and then Dr. Vikram Rao to wrap up this session with their comments.
So this is a wrap up, which also means the lateness of the evening. Professor Raghu and I decided to halve the time that we were previously given. I'm sure this comes as a great relief to most of you. And I think we can get it done in that time. So my part of the job was to give a brief recap of what happened. And there's not a lot to be said, but I had a couple of takeaways. I don't think we had many surprises. So we mapped this out. Originally, the team mapped this program out based upon what we saw as a existential threat priority. And we mapped it out on a belief. As stated, was something like this, that if you solve it for India, you solve it for the world, something of that sort. And after going through the 3 days, see, I would have to say that I don't have much cognizance of the Indian scene. I got much better of it now, and I do have some cognizance of the international scene. And I would say, based upon what I saw and heard, that pretty much holds water in the entire spectrum of what we saw. The other thing is that I didn't see many gaps. I mean, it's kind of fairly extraordinary that when you look at the entire sector of carbon mitigation and say what all needs to be done, it's fairly extraordinary that that horsepower, by and large, is available here. But the by and large is a good bit, because if we were fully self-sufficient, then we wouldn't need the collaboration of others, which would sort of militate against the principles of consortia. So I would say the fact that, and I'll point out 1 or 2 of the gap areas that we have, it almost compels us into us being the consortium, into collaboration. And I would say that the collaboration would be in part with industry, but also in fairly large part the entities in other countries, which of course is also one of the basic imperatives of the Institute of Eminence direction. So it all fits. And not that it matters much, but one of the areas that we have no effort is in the nuclear area, particularly in small modular reactors, which was incidentally mentioned by a few folks, and which is a personal favorite of mine as something of the future. The Department of Energy at US have identified that. In fact, the US Energy Secretary spoke specifically to that point, and I was surprised when she spoke about modular reactors in Glasgow. But so that's one. But these are examples only. The point is that these so-called gaps is actually a good thing, because it, as I said, persuades us. The other thing that surprised me surprised me initially, and then I said, yeah, it makes sense, was the consular presence. It's not something I expected, let's put it that way. And I think that what it probably says is that we got the timing right on this deal. And what does that mean? In other words, we got this consortium and the associate symposium kicking off at a time, and with the topic that we had, kicking off at a time when governments are caring suddenly. Governments have made promises in Glasgow that they might be still figuring out how to keep, including the Indian government. So it's sort of a good time to be in research, but I want to finish with one thought. It's a great time to be in research, but it's also a great time for us in engineering to understand the place of policy. To understand economics we get. It's the policy part that we probably don't get to the extent that we should. And something that we will fix down the road to actually inculcate it within the consortium. But right now, it encourages collaboration. So anyway, so these are some of the thoughts. Raghu, take it away on the future.
Thank you, Vikram. And the person most relieved about us deciding to do it in 10 minutes was me, one of the audience. So I'm really happy. I think it's a great beginning for the consortium. But right before we started this, and of course, I just want to shout out to the wonderful organization of our team from the Office of Global Engagement. If you can believe that we really started in right earnest only about 3 weeks or a month before this, and we have done this. It's just remarkable, and people who have done this know who they are. So I just want to first say that and thank you. When we started this, I was a little worried about how it will go, but I pretty much knew this meeting will be well done. But my worry always about anything that starts in India, we know how many bridges are still being built in India, right? So my worry is not about this consortium as an administrator, if I take the administrator's hat. It's about the follow-up. It's about what do we do from now on? Can we have something in a year from now where we have something like a tech summit, where we have some pilot demonstrations, where people can come and see what we have talked about here? How do we get from here to there is the only question that occupies my mind, nothing else. And I think in India, I think it's very difficult for us. I still think, though things have changed a lot, to really consolidate and collaborate and have that big picture in mind and do that within a time frame. So I am going forward. What I would like to do is brainstorm with all of you to see ways in which we work so that we don't lose this momentum. We have very clear plans for what we are going to do going forward. Have meaningful plans, which like everyone says, we also can make some promises and live up to those promises. So I will be reaching out to many of you who have come today to partner with us. And hopefully we can all partner together and work on the ideas that we have deliberated here and do something meaningful for the country in general and the global society. So that's what I would hope for. And I thank all of you for participating. And I expect that you will help us, partner with us, counsel us in going forward, and then at least reaching to some level of maturity in some of these technologies in a short order, not 10 years. I don't have that kind of time. None of us have that kind of time. So year or two, we should have a consortium at IIT Madras, which is global presence. Thank you very much, all of you. Sanjeeva, thank you so much for being here. Sorry, it's just too late. I'm sure the audience would have liked to ask you a lot of questions, but given the time constraints, we couldn't take any questions. But we will surely be reaching out to you. And also the very methodical way in which your country works. I hope some of that we adopt here, both at an institute level and also nationally. Thank you for sharing your insights.
Sanjeev, I've asked Amy for a copy of that key slide that you had, which actually shows dollar figures. And I was hoping they were Australian dollars. I was hoping they were US dollars, because Australian dollars, those numbers are going to be very challenging. But so Amy will get me the slide. Thank you.
Thank you, professors. Thank you for having me. And I look forward to working with you.
Thank you, Professor Raghu. Thank you, Dr. Vikram. So once again, I would like to thank you all, the participants, students, professors, researchers, scientists, policy makers, industrialists, and our friends from the consulates, volunteers and organizers who made this event a grand successful one. And I would like to dedicate a Tirukural again to you. முயற்சி திருவனையாக்கும் முயற்றின்மை இன்மை புகுத்திவிடும். So this is a start and this is an effort. And we promise the team from IIT Madras will work efficiently and effectively for a better world tomorrow. Let's just join hands to do this. Jai Hind. Thank you.